Please subscribe to support the channel. The universe occasionally reminds us just how vast and mysterious it truly is. For centuries, humanity believed that comets and asteroids were strictly local residents of our solar system, born alongside the planets and eternally bound by the sun's gravity. Yet in recent years, astronomers have discovered something far more extraordinary: travelers that did not originate here at all. These cosmic interlopers, known as interstellar objects, have crossed the unimaginable gulfs between stars to briefly pass through our neighborhood before vanishing back into the darkness of space. One such visitor, discovered in 2019, has sparked intrigue, debate, and curiosity among scientists. It was given the official name 3I Atlas, making it the third interstellar object ever detected within our solar system. 3I Atlas stands as a testament to how far astronomy has advanced, and at the same time, it represents how much we still do not know. Unlike many asteroids or comets that spend millions of years orbiting the sun, interstellar objects come in once, swing by at breathtaking speeds, and then leave forever. They offer us a fleeting chance to study the building blocks of distant star systems, worlds that we may never reach with spacecraft but can momentarily touch through these natural messengers. What makes 3I Atlas particularly fascinating is its mysterious nature. Unlike its predecessors, the famous 1I ʻOumuamua and 2I Borisov, this object was far dimmer, far more elusive, and ultimately far harder to study. Yet even with limited data, its discovery underscored the fact that interstellar visitors are not once-in-a-lifetime anomalies. They may be far more common than we ever imagined. Each one, no matter how faint or brief, is a clue to the greater story of our galaxy's evolution. So when we talk about the strange case of 3I Atlas, we're really talking about more than just a comet-like body zipping through our skies. We're talking about a messenger from another star, an opportunity to peek into the chemical and physical processes that shape planetary systems far beyond our sun. And although its faintness left scientists with far more questions than answers, it still represents a milestone in the history of astronomy. Proof that we are beginning to enter an age where detecting interstellar objects may become routine rather than rare. This is the story of 3I Atlas, the third known interstellar object in our solar system, a visitor from another world, and a symbol of the mysteries that still await us in the stars. When astronomers use the word interstellar, they're describing something that originates between the stars, outside of our solar system. To understand why this is such a big deal, it helps to step back and think about what most of the objects we usually study actually are. The majority of small bodies in space, asteroids, comets, and meteoroids, are leftovers from the early formation of our solar system about 4.6 billion years ago. They were born from the same giant disk of dust and gas that created the sun, the planets, and everything else bound to our star's gravity. These objects stay trapped in stable orbits around the sun, cycling endlessly through predictable paths in the asteroid belt, the Kuiper belt, or even the distant Oort cloud. Interstellar objects, however, are fundamentally different. They did not form in our solar system at all. Instead, they are cosmic drifters, likely ejected from other star systems billions of years ago. Picture a young planetary system under construction. Giant planets tugging on planetesimals, icy bodies colliding and scattering, and debris flying outward in every direction. In many cases, the gravitational dance of giant planets can sling smaller bodies outward with enough speed that they escape their home star completely. Once that happens, the object becomes a permanent wanderer of interstellar space, drifting silently between stars for eons. Some of these nomads eventually stumble into other systems, ours included. This is why astronomers treat interstellar visitors with such awe. When one enters our solar system, it's not just another asteroid or comet, it's literally an emissary from another star system. For a brief window of time, humanity gets the chance to study material that was formed under completely different conditions, influenced by a different star, and shaped by alien planetary dynamics. To put it simply, these objects are natural samples from other parts of the galaxy, delivered right to our doorstep. Another reason they are so unique lies in their trajectories. Most comets and asteroids orbit the sun in ellipses. Some have highly stretched orbits, but they are still closed loops, they always come back. Interstellar objects, on the other hand, follow hyperbolic orbits, which means their paths are open curves. Instead of being bound to the sun's gravity, they simply curve around it and keep going. The fact that they are moving too fast to remain captured is the giveaway that they come from beyond our solar system. The differences go deeper than just their origins and trajectories. Interstellar objects also challenge our understanding of planetary formation itself. For instance, ʻOumuamua, the first interstellar object discovered, didn't behave quite like a comet or an asteroid. It lacked a clear tail but still showed non-gravitational acceleration, hinting at outgassing or some other unfamiliar mechanism. This baffled scientists and sparked intense debate about what interstellar objects might actually be made of. When Borisov came along, it looked much more like a typical comet, complete with a coma and tail, but its chemical composition raised new questions about diversity in other star systems. In that sense, every new interstellar detection is like opening a new chapter in an unfolding mystery. Each one provides a unique data point, a clue about the types of materials and processes happening in star systems across the Milky Way. When 3I Atlas was detected, despite being faint and frustratingly hard to study, it still confirmed something critical. These objects aren't one-off flukes. If we've already spotted 3 in just a few years, there could be thousands or even millions silently passing through the solar system on scales of centuries or decades. Why does this matter beyond scientific curiosity? Because studying interstellar objects directly links us to the larger galaxy. Imagine trying to understand how life might arise elsewhere. To answer that, we need to know about the chemistry of other planetary systems. Sending spacecraft to other stars is technologically unfeasible for now, but when interstellar objects come to us, they provide direct evidence of the kinds of ices, dust, and rock forming around other suns. They are like bottled messages tossed into a cosmic ocean, carrying information across light years, waiting for us to intercept them. There's also a poetic side to it. When you look at a comet in the night sky, you're seeing something local, something that's been circling the sun since long before humans existed. But when you glimpse an interstellar visitor, if you're lucky enough, you're looking at an alien piece of matter that has journeyed for perhaps millions of years through the cold void, across unimaginable distances, and finally crossed paths with Earth. It is the closest thing to shaking hands with another star system without leaving home. In summary, the word interstellar isn't just a classification, it represents a completely different category of object. While comets and asteroids are like members of our solar family, interstellar visitors are strangers from faraway lands. They are rare, precious, and fleeting, but they hold the potential to expand our understanding of the galaxy in ways no local asteroid ever could. And with each one we discover, we're reminded that our solar system is not isolated. It is part of a larger cosmic community, constantly exchanging material across the stars. The discovery timeline of 3I Atlas is as fascinating as the object itself, not only because of the technical achievement required to detect such a faint traveler, but also because it highlights how astronomy has entered a new era of interstellar discovery. To appreciate the timeline properly, we need to look at the broader context. Detecting faint moving objects in the night sky is not easy, and catching an interstellar one is like spotting a single raindrop in a storm. These objects are often dim, fast-moving, and visible for only a short time before vanishing into the depths of space. That was exactly the case with 3I Atlas. The story begins in 2019, when astronomers operating the Asteroid Terrestrial Impact Last Alert System, ATLAS, in Hawaii were scanning the skies. ATLAS is a survey program designed to detect potentially hazardous asteroids, objects that could one day impact Earth. Instead of looking specifically for interstellar visitors, it's constantly scanning wide patches of the sky for anything new or moving. On June 9, 2019, the system detected a faint, moving point of light that didn't seem to match any known asteroid or comet. At the time, it was catalogued as C2019Q4, Atlas, under the assumption that it was a comet. Initially, its trajectory wasn't immediately recognized as unusual. When astronomers first spot a new object, they collect a handful of observations, essentially positions against the background stars, and use those to calculate its orbit. With only a few data points, the orbit is uncertain, and it can take days or weeks of follow-up observations to refine. But as the measurements of this new object accumulated, its orbit began to look strange. The calculations showed that it wasn't following a closed elliptical path like an ordinary comet. Instead, its orbit was highly hyperbolic, with an eccentricity greater than 1. This was the first red flag that the object might be interstellar. By late summer 2019, astronomers confirmed what the orbit suggested. The object was not bound to the Sun. It had entered the solar system from interstellar space and would eventually leave again. This made it only the third interstellar object ever detected, following 1I ʻOumuamua in 2017 and 2I Borisov in 2019. Once the interstellar nature was confirmed, its designation was updated to 3I Atlas, the 3I marking it as the third interstellar discovery, and Atlas crediting the telescope system that first spotted it. The timeline of its discovery is notable because of how quickly astronomers had to act. Interstellar objects don't stick around. They speed through the solar system at tens of kilometers per second, and if you miss the observation window, they're gone forever. Unfortunately, 3I Atlas was faint right from the beginning, which meant it was only observed for a short period before fading beyond the reach of even the largest telescopes. Despite this, the handful of observations gathered were enough to confirm its interstellar nature. The entire discovery unfolded in less than a few weeks. A June 9, 2019, first detected by Atlas in Hawaii. A following weeks of June and July 2019, additional observations collected by astronomers worldwide. A later in 2019, orbit calculations confirmed a hyperbolic trajectory, cementing its classification as an interstellar object. Air 2020, officially redesignated as 3I Atlas. It's also worth noting how serendipitous this discovery was. Atlas was not designed to hunt for interstellar objects specifically. It was designed to catch Earth-threatening asteroids. But because of its wide sky coverage and frequent scans, it was able to pick up something as rare and fleeting as 3I Atlas. Without this kind of modern survey technology, there's a very good chance the object would have passed through undetected, joining the countless others that have likely come and gone without our notice. In many ways, the discovery timeline of 3I Atlas underscores just how challenging it is to spot these interstellar wanderers. Even though we now know they're not as rare as once believed, they still move quickly, fade fast, and demand almost immediate follow-up. The fact that Atlas caught this one at all is a reminder that the right technology, operating persistently, can catch surprises, even when it isn't specifically looking for them. The story of 3I Atlas cannot be told without diving into the remarkable system that made its discovery possible: the Asteroid Terrestrial Impact Last Alert System, better known by its acronym ATLAS. This network of telescopes has quietly become one of humanity's most important guardians in space, constantly scanning the skies not only for cosmic wanderers like interstellar objects, but also for threats that could potentially collide with Earth. Its mission combines planetary defense, deep sky monitoring, and, through cases like 3I Atlas, unexpected contributions to the frontier of interstellar science. ATLAS was developed by the University of Hawaii's Institute for Astronomy, with funding from NASA's Planetary Defense Coordination Office. Its original purpose was straightforward but vital: to act as an early warning system for asteroids on a collision course with Earth. While large, catastrophic asteroids are relatively rare, smaller ones, still capable of causing serious regional damage, are far more common. Many of these smaller asteroids remain undetected until they are already very close, as was the case with the Chelyabinsk meteor that exploded over Russia in 2013. ATLAS was created to change that by providing days or weeks of warning for asteroids that might otherwise slip through unnoticed. The ATLAS system consists of multiple telescopes strategically located across the globe. The original 2 telescopes were installed in Hawaii, one on Haleakala, Maui, and the other on Mauna Loa, Big Island. Later expansions added sites in South Africa and Chile, creating a near-global coverage network. Each telescope is modest in size compared to some of the world's largest observatories, with an aperture of 0.5 meters, about 20 inches, but what they lack in size they make up for in wide field capability. Each telescope can cover an extremely wide portion of the sky, about 30 degrees across in a single exposure. This wide field design allows ATLAS to sweep the entire visible sky every 2 nights, providing comprehensive coverage and rapid detection of any moving objects. ATLAS is fully robotic and automated. It takes repeated images of the same patch of sky and uses specialized software to detect anything that moves relative to the background stars. Once a candidate object is flagged, the system calculates its orbit and quickly determines whether it poses any threat to Earth. If it does, the information is shared with the global astronomy community and emergency organizations to prepare potential responses. The detection of 3I Atlas in June 2019 was a perfect example of Atlas doing its job, but with an unexpected twist. While the system was searching for near-Earth asteroids, it instead stumbled upon a faint, fast-moving object with an unusual trajectory. At first, it looked like a comet, which is not uncommon in wide-sky surveys. But after follow-up observations revealed the hyperbolic orbit, astronomers realized that this was not an ordinary comet at all, but an interstellar visitor. In other words, Atlas had unintentionally discovered a piece of another star system. What's significant here is that Atlas, by design, prioritizes speed and coverage over depth. Unlike giant telescopes such as the Keck Observatory or Hubble Space Telescope, which can peer incredibly deeply into space but only at tiny patches of sky, Atlas excels at looking everywhere, all the time. This makes it uniquely suited to catch transient events, things that appear suddenly and might be gone in days or weeks. Interstellar objects like 3I Atlas are exactly that kind of fleeting phenomenon. Another important point about Atlas is that it plays a dual role in science and safety. On the safety side, it has already proven its worth by detecting small asteroids hours to days before they pass close to Earth, providing reassurance that humanity now has at least some level of planetary defense capability. On the science side, its data contributes to everything from supernova discoveries to near-Earth asteroid tracking to, in this case, capturing evidence of interstellar visitors. The fact that a system designed to prevent disasters on Earth can also contribute to answering profound questions about the galaxy is part of what makes Atlas so fascinating. It shows how tools built for one purpose can often unlock doors in entirely unexpected areas of science. Without Atlas, 3I Atlas would likely have passed through our solar system without ever being noticed, joining the countless unseen interstellar travelers that slip by every year. In essence, Atlas is the quiet sentinel of the skies. It is not the most glamorous or powerful observatory on Earth, but it is one of the most effective at protecting us and, occasionally, gifting us with glimpses of wonders from beyond the solar system. The discovery of 3I Atlas is a shining example of its success. A system designed for planetary defense ended up giving us another piece of evidence that our solar system is not an isolated island, but part of a much larger cosmic network. When astronomers discover a new object in the sky, especially one as unusual as an interstellar visitor, it's not enough to simply say, "We found something." It needs a name, a formal designation that tells the scientific community not only what it is, but also when and how it was discovered. The naming conventions might sound complicated at first, but they serve an important role. They create a universal system of communication. Without it, the thousands of comets, asteroids, and other celestial bodies discovered each year would quickly become a confusing mess. In the case of 3I Atlas, the name itself tells us a complete story. Let's break it down. 3I. The I stands for interstellar. This designation is given only to objects confirmed to have originated outside of our solar system. The number 3 means it was the third such interstellar object ever discovered. The first was 1I ʻOumuamua, detected in 2017. The second was 2I Borisov, discovered in 2019. That places 3I Atlas as the third chapter in this unfolding saga of interstellar discoveries. Atlas. This part of the name credits the survey system that first detected the object, the Asteroid Terrestrial Impact Last Alert System in Hawaii. By tradition, newly discovered comets and interstellar objects often carry the name of the telescope, survey program, or individual astronomer who made the discovery. In this case, Atlas received the honor because its wide-sky scanning system caught the faint intruder first. But there's more nuance here, because before an object is confirmed to be interstellar, it is given a provisional designation based on the system used for comets. When 3I Atlas was first observed in June 2019, it was initially named C 2019 Q4, Atlas. Let's unpack that. The C indicates that it was thought to be a comet, since it displayed a slightly fuzzy appearance resembling a coma. 2019 is the year of discovery. A Q4 means it was the fourth comet discovered in the second half of August 2019. The letters progress through the year, with Q referring to the half-month of August 16th to 31st. And, again, Atlas credited the discovery team. So originally, astronomers thought they were simply adding another comet to the long catalogue of known comets. Only later, after precise orbital calculations showed its trajectory was hyperbolic and interstellar in origin, was its designation updated to 3I Atlas. The I classification is relatively new in astronomy and was first introduced by the International Astronomical Union, IAU, in 2017, when ʻOumuamua was discovered. Before then, Astronomers didn't have a specific system in place to name interstellar objects, simply because none had ever been observed. ʻOumuamua forced a change, creating a new category that 3I Atlas would eventually join. This naming system is more than just a label. It reflects the extraordinary rarity of these detections. Out of the millions of catalogued small bodies in our solar system, only 3 carry the I designation. It's a badge of uniqueness, instantly telling astronomers around the world that they're dealing with something from beyond the sun's domain. It's also worth noting that the names often carry symbolic weight. ʻOumuamua, for example, was given a Hawaiian name meaning scout or messenger from afar, reflecting both its place of discovery and its role as the first identified interstellar traveler. Borisov was named after Gennady Borisov, the amateur astronomer in Crimea who spotted it. Atlas, in turn, takes its name from the system, but the word also carries a mythological resonance. Atlas was the titan who held up the heavens, a fitting nod to a telescope system watching the skies. So, when we say 3I Atlas, we're saying far more than just a name. We're invoking a discovery timeline, a classification system, a recognition of the technology that spotted it, and a place in the growing list of humanity's encounters with objects from other star systems. It is, in essence, the object's identity card, a shorthand way of telling its story every time the name is spoken. When we place 3I Atlas side by side with 1I ʻOumuamua, the very first interstellar object ever discovered, the comparison is both illuminating and perplexing. Both are interstellar visitors, rare emissaries from beyond our solar system. But the way they revealed themselves, and the scientific puzzles they left behind, couldn't be more different. If ʻOumuamua was the enigmatic celebrity guest that captured the imagination of the entire world, then 3I Atlas was its faint, elusive cousin, slipping quietly into the solar system stage before vanishing almost unnoticed. Let's look more closely at how the two compare. ʻOumuamua was discovered in October 2017 by the Pan-STARRS 1 telescope in Hawaii. It was a groundbreaking moment, the very first time astronomers had ever detected an object conclusively proven to come from outside the solar system. Its hyperbolic orbit, with an eccentricity of about 1.2, made it clear it was not gravitationally bound to the Sun. Its discovery was a shock because for decades astronomers suspected interstellar objects might exist, but until then, they had never been observed. By contrast, 3I Atlas, discovered in June 2019, arrived at a time when astronomers were already alert to the possibility of spotting more interstellar visitors. ʻOumuamua had shown that these objects exist and can be detected, so surveys like Atlas were naturally on the lookout, even if not explicitly designed for the task. However, unlike ʻOumuamua, 3I Atlas was faint and short-lived in visibility, meaning it did not make the same splash in the scientific community or public imagination. One of the biggest differences between the two lies in how easy, or difficult, they were to observe. ʻOumuamua, though small, estimated only a few hundred meters long, it was relatively bright compared to 3I Atlas, allowing astronomers several weeks of observation before it faded beyond reach. This gave scientists time to collect light curves, measure its motion precisely, and even debate its shape and possible origin. Its unusual brightness pattern, which hinted at a cigar-like or pancake-like elongated body, made it one of the most intriguing space objects ever studied. 3I Atlas. In stark contrast, it was extremely faint right from the beginning. Even at its brightest, it was barely detectable with mid-sized telescopes, and it faded so quickly that astronomers had only a narrow observational window. This faintness limited the amount of data collected, leaving large gaps in our understanding of its properties. If ʻOumuamua gave us a tantalizing mystery full of strange clues, 3I Atlas left us with little more than a shadowy outline. One of the most famous mysteries of ʻOumuamua was its shape. Its light curve showed dramatic variations, suggesting it was either highly elongated like a cigar or flat like a pancake. No asteroid or comet previously observed in our solar system had ever shown such extreme elongation. On top of that, it displayed non-gravitational acceleration. Its motion slightly deviated from the path predicted by gravity alone, as though something were giving it a small push. Normally, comets do this when sublimating ices create jets of gas, but ʻOumuamua didn't show a visible coma or tail. This left scientists puzzled. Was it a comet unlike any we'd seen before, or something else entirely? For 3I Atlas, we never obtained enough data to answer similar questions. Its faintness prevented astronomers from building a detailed light curve, so we don't know its shape. It didn't provide enough evidence of non-gravitational acceleration either, so it didn't ignite the same kind of heated debates. In this sense, 3I Atlas was less of a mystery, but only because we had fewer clues to work with. It was like glimpsing a stranger in a crowd versus having a long, strange conversation with one. Oumuamua's size was estimated to be somewhere between 100 and 400 meters in length, depending on its reflectivity. 3I Atlas was thought to be somewhat similar in scale, but because of its faintness, size estimates were far less precise. Some models suggest it could have been a few hundred meters wide, possibly similar to Oumuamua. The key difference lies in the confidence of those measurements. For Oumuamua, we had weeks of brightness data to refine size models, while for 3I Atlas, astronomers were working with scraps of information. Here's where the comparison becomes dramatic. Oumuamua was a cultural phenomenon. Its odd shape and unexplained acceleration led to waves of speculation, including theories that it might be an alien probe or an artificial object. Scientists like Avi Loeb argued in favor of these ideas, sparking global debates that reached far beyond astronomy circles. The media frenzy turned Oumuamua into a household name. 3I Atlas, however, barely made headlines. Because it was faint, short-lived, and lacking in unusual behavior, it didn't inspire the same excitement. While scientists were thrilled to add another interstellar object to the list, the public barely noticed. This contrast is telling. Not every interstellar object will be a headline-grabbing mystery. Some, like 3I Atlas, will slip by quietly, offering only modest insights. Despite these differences, both objects share one fundamental similarity. They confirm that interstellar objects are real and detectable. Oumuamua was the first proof of concept, the unexpected discovery that shocked the scientific community. 3I Atlas, though faint, reinforced the idea that interstellar visitors are not once-in-a-lifetime anomalies. They are part of the natural fabric of our galaxy. Each detection increases our understanding of how common such objects might be, and helps refine models of planetary system formation and dynamics. In a way, Oumuamua was the flamboyant trailblazer, the object that forced us to create an entirely new naming system and open the door to new theories. 3I Atlas, by contrast, was quieter but no less important. It added weight to the argument that many more such objects are out there, waiting to be found by future surveys. So, when comparing the two, the story becomes clear. Oumuamua gave us more questions than answers, a cosmic riddle that still stirs debate. A 3I Atlas gave us confirmation and perspective, a reminder that interstellar visitors are not isolated miracles but recurring phenomena. Together, they represent different sides of the same cosmic coin, one dazzling and controversial, the other faint but steady, both pointing toward a future where interstellar science may become routine rather than extraordinary. When we compare 3I Atlas with 2I Borisov, the second interstellar object ever discovered, we see another fascinating contrast, one that highlights just how diverse interstellar visitors can be. While 2I Borisov was clear and unmistakable in its comet-like behavior, 3I Atlas was faint, fleeting, and ultimately far more mysterious. Both traveled through our solar system from the distant reaches of interstellar space, yet they left behind very different impressions. Borisov was discovered in August 2019 by amateur astronomer Gennady Borisov, who used his custom-built telescope in Crimea to spot it. From the very beginning, its identity was obvious. It displayed the classic features of a comet, including a coma and a tail of gas and dust streaming away from its nucleus. This meant scientists could study it using the same techniques they apply to comets within our solar system, analyzing its composition and activity. In fact, 2I Borisov behaved so much like an ordinary comet that it was often described as a comet from another star. This gave astronomers a unique opportunity. They could directly compare it to the comets we know and ask whether planetary systems across the galaxy produce similar kinds of icy bodies. 3I Atlas, in contrast, was much less cooperative. Although it was initially catalogued as a comet, it never displayed the same obvious coma or tail as Borisov. Its faintness made it incredibly difficult to observe in detail, and astronomers had only a short time to gather data before it faded away. While Borisov gave us a wealth of information, spectral data, compositional details, even high-resolution images from large telescopes, 3I Atlas left us with little more than confirmation of its hyperbolic orbit. The The difference in the amount of data available between the two is stark. Borisov's passage was like hosting a guest who stayed for dinner and conversation, while Atlas was more like a stranger who brushed past you in a crowd, leaving only the faintest impression. The comparison becomes even more striking when we look at brightness. Borisov was bright enough that astronomers all over the world could follow it with ease, some even using medium-sized amateur telescopes to capture images. It remained observable for several months, giving researchers time to track its behavior as it approached and then receded from the Sun. By contrast, 3I Atlas was faint from the moment it was spotted, requiring professional observatories to gather what little data they could. Its faintness and rapid disappearance made it almost invisible to the broader astronomy community, much less the public. Yet, despite these differences, both objects serve as critical points of comparison. Borisov taught us that at least some interstellar visitors closely resemble the icy comets of our own solar system. Its ice is sublimated under sunlight, releasing gases like cyanogen and water vapor, which were detected and analyzed. That told us something profound. The chemistry of planet-forming disks around other stars can produce comet-like bodies strikingly similar to ours. 3I Atlas, by contrast, showed us the limits of our observational capability. It reminded scientists that not every interstellar object will be cooperative or easy to study. Some will be too faint, too small, or too fast to yield much information, even with modern instruments. In that sense, Borisov represents the richness of data we can hope for, while Atlas represents the challenge we must overcome. Another interesting aspect is the public and scientific reception. Borisov's comet-like nature made it instantly recognizable and scientifically valuable, and it quickly gained attention as the first real interstellar comet. Major observatories turned their eyes toward it, and it became the subject of numerous studies. 3I Atlas, by comparison, barely registered beyond dedicated research circles. It lacked the spectacle of Borisov's glowing tail or the intrigue of ʻOumuamua's mysterious acceleration. As a result, it quietly slipped into the record books without the same fanfare. The contrast between Borisov and Atlas also underscores the enormous diversity likely present in interstellar objects. Some, like Borisov, may look familiar and allow direct comparisons with known bodies. Others, like Atlas, may be strange and unyielding, providing only hints of their true nature. The fact that the first three interstellar objects we've discovered are all so different, ʻOumuamua being enigmatic and unprecedented, Borisov being comet-like and familiar, and Atlas being faint and frustrating, suggests that interstellar visitors come in many forms, shaped by the chaotic processes of countless alien star systems. Ultimately, 2I Borisov and 3I Atlas together represent two ends of a spectrum. Borisov gave us clarity and answers, while Atlas gave us questions and mystery. Both, however, remind us of the importance of vigilance. The galaxy is full of these wandering bodies, and each one, whether bright or faint, is a messenger carrying information about distant worlds. When astronomers talk about what makes an interstellar object truly interstellar, the most important clue is not how it looks, how bright it is, or even whether it has a tail. The defining evidence lies in its orbit. For 3I Atlas, the giveaway was that it followed a hyperbolic trajectory, something fundamentally different from the ellipses and circles that bind most objects in the solar system. To understand why this matters, we need to look more closely at orbital mechanics and how astronomers determine whether something is native to our solar system or just passing through. In simple terms, most small bodies in our solar system, asteroids, comets, even the icy objects far out in the Oort cloud, travel around the Sun in elliptical orbits. An ellipse is a closed path, meaning the object will always return after a set period of time. The eccentricity, which measures how stretched out an orbit is, ranges between 0, a perfect circle, and just under 1, a very elongated ellipse. No matter how stretched, if the eccentricity is less than 1, the orbit is bound to the Sun. But once the eccentricity reaches greater than 1, the path is no longer a closed loop, it becomes a hyperbola, which is an open curve. A body on a hyperbolic orbit comes in from far away, swings around the Sun once, and then heads back out into space, never to return. This is the orbital signature of an interstellar object. It's a kind of cosmic one-way ticket. The object is moving too fast for the Sun's gravity to capture it. 3I Atlas showed precisely this kind of trajectory. Its eccentricity was calculated to be significantly greater than 1, firmly placing it on a hyperbolic path. That meant it wasn't a long-period comet returning after millions of years from the Oort cloud, but rather something that had entered the solar system from beyond. The shape of its orbit told the story of an interstellar traveler that had likely been drifting between stars for countless millennia before chance brought it past our Sun. Another important factor is velocity. Objects bound to the Sun, even those in the distant Oort cloud, have speeds limited by the Sun's gravitational well. But interstellar objects like 3I Atlas come in with what's called an excess hyperbolic velocity, a speed that is higher than what solar system objects could ever achieve naturally from orbital dynamics alone. In other words, even if you rewound its path, there's no way it could have originated within the Sun's gravitational influence. The speed itself is proof that it was born elsewhere. The orientation of its path also told astronomers something important. Unlike planets, which orbit roughly within the same flat plane known as the ecliptic, 3I Atlas cut through the solar system on a tilted trajectory. This was another clue pointing to its alien origin. Objects formed in the solar system tend to share the Sun's angular momentum and orbital plane, but interstellar visitors can come from literally any direction in the sky. They are like stones tossed randomly into a pond, each splash tracing its own angle. It's worth pausing here to imagine what that actually means. For billions of years, 3I Atlas had likely been traveling alone in the cold void between stars. No light from its home star warmed it. It was simply coasting, perhaps ejected from a distant planetary system long ago, perhaps after a gravitational tug from a giant planet threw it outward. Eventually, after drifting for who knows how long, maybe millions of years, it happened to pass near enough to our Sun to be noticed. And then, just as quickly as it arrived, it bent around the Sun on its hyperbolic course and continued its endless journey into the galactic night. The significance of this hyperbolic orbit cannot be overstated. Without it, 3I Atlas would just be another faint comet. With it, it became one of the rarest kinds of objects ever identified, an interstellar messenger. For astronomers, this orbital evidence is the equivalent of a fingerprint. No tail, no brightness curve, not even composition data is required. The math of the orbit alone proves its origin. It is the most unambiguous indicator that what we are looking at did not form here. In the case of 3I Atlas, the orbital calculations were not as precise as for 1I ʻOumuamua or 2I Borisov, largely because of how faint and short-lived it was in our telescopes. Still, even with limited data, the trajectory was clear enough to establish its hyperbolic nature. That's why, despite the lack of other details, astronomers were confident enough to give it the official interstellar designation. So when we say that 3I Atlas followed a hyperbolic orbit, we're saying that the Sun was merely a pit stop on its endless journey through the galaxy. It entered our solar system, curved around the Sun in a brief celestial encounter, and then left. Forever. This one fleeting arc across our skies is all we will ever see of it. The speed of 3I Atlas is one of the most defining aspects of its story, because velocity is not just a number in orbital mechanics, it's the smoking gun that proves whether something is interstellar or local. When astronomers calculated its motion, they found that it was traveling far faster than any comet or asteroid born in our solar system could naturally achieve. That speed, coupled with its hyperbolic trajectory, made it clear this was no homegrown comet, but a true visitor from the stars. To understand why speed is so important, let's look at how objects usually move in the solar system. Every planet, asteroid, and comet is bound to the Sun's gravity, and their speeds are dictated by how close they are to the Sun and how far they travel in their elliptical orbits. For instance, Earth orbits the Sun at about 30 kilometers per second. Typical comets, when they swing in from the distant Oort cloud, move faster, sometimes reaching speeds of 40 to 50 kilometers per second near perihelion, their closest point to the Sun. But even those comets, traveling at breathtaking speeds, are still bound to the Sun. They'll slow down as they head back out and eventually return after thousands or millions of years. An interstellar object is different. It comes in carrying extra velocity, what astronomers call hyperbolic excess velocity. This is the speed it still has left over after escaping the gravitational pull of its home star system, and it ensures that when it passes near our Sun, it won't be captured. Instead, it simply curves around the Sun and flies off again, forever unbound. For 3I Atlas, its predicted incoming speed was around 30 kilometers per second relative to the Sun before it even approached our system. This alone was unusual, because it matched the typical galactic orbital speeds of stars and objects moving through the Milky Way. By the time it reached perihelion, its closest approach to the Sun, it was moving much faster, closer to 60 kilometers per second. That's almost twice the speed of Earth's orbital velocity, and more than enough to escape the Sun's gravity once it passed. What's remarkable is that this speed is entirely consistent with what we would expect from an interstellar object. The stars in our galaxy orbit the center of the Milky Way at different speeds, and smaller bodies ejected from those star systems inherit similar motions. Astronomers have calculated that random interstellar objects passing through the solar system should have velocities in the range of 20 to 70 km per second relative to the Sunday 3I Atlas fits neatly within this expected range, further cementing its status as an interstellar traveler. It's worth contrasting this with 1I ʻOumuamua and 2I Borisov, whose speeds were also measured with great interest. ʻOumuamua came in with a hyperbolic excess velocity of about 26 km per second, while Borisov clocked in at around 32 km per second. 3I Atlas, with an excess speed in the same ballpark, aligns perfectly with this emerging pattern. These numbers tell astronomers that such visitors are not anomalies. They are part of a larger galactic population of wandering debris, drifting through interstellar space at typical stellar speeds. The velocity of 3I Atlas also has deeper implications. It suggests that the object was likely ejected from its home star system through gravitational interactions, most probably with a giant planet. In young planetary systems, newly formed gas giants can act like cosmic slingshots, hurling smaller bodies outward with enough speed to break free completely. Over millions of years, countless such ejections occur, filling the galaxy with rogue comets and asteroids. 3I Atlas was one such castaway, and its high speed was the permanent reminder of the violent gravitational tug-of-war that launched it into interstellar space. There's also a poetic aspect to this. Imagine 3I Atlas drifting in the emptiness between stars for millions of years, traveling tens of kilometers every second, unbothered and unseen. At that relentless pace, it could cross the distance between stars in just a few million years, a blink of an eye on cosmic timescales. To us, its speed is almost incomprehensible, but in the galaxy, this kind of motion is simply the norm. Stars themselves move at similar velocities around the galactic center, and their ejected debris follows suit. The speed also explains why these objects are so difficult to study. Even with the best telescopes, astronomers have only a short window of opportunity to observe them before they disappear forever. In the case of 3I Atlas, its faintness combined with its rapid pace meant that only a few brief observations could be gathered. By the time scientists confirmed its hyperbolic trajectory, it was already slipping away into the void, untouchable. So, the velocity of 3I Atlas was both its signature and its curse. It proved beyond doubt that the object was interstellar, yet it also guaranteed that our encounter with it would be short and fleeting. In the end, its speed was not just a number. It was the story of its birth, its journey, and its inevitable departure, written in the mathematics of motion. One of the most elusive details about 3I Atlas is its size. When astronomers look at objects within the solar system, especially asteroids or comets, they usually have several methods to estimate their dimensions. But with 3I Atlas, those methods quickly ran into major challenges. Its faintness, its rapid speed through the solar system, and the limited time window for observation all conspired to make its true size difficult to pin down. Yet, even with these difficulties, scientists were able to come up with educated guesses, and those guesses revealed something interesting about the nature of this interstellar visitor. The first and most common way to estimate the size of a distant object is by measuring its apparent brightness, the amount of light it reflects from the sun. The brighter an object appears at a given distance, the larger it is likely to be. However, this method depends on another key factor, albedo, which is the reflectivity of its surface. A dark, carbon-rich surface reflects very little sunlight, meaning the object would appear faint even if it were relatively large. On the other hand, a bright, icy surface reflects a lot of light, making the same-sized body look far more luminous. Since astronomers had no direct way of knowing the albedo of 3I Atlas, any size estimates came with large uncertainties. Despite these uncertainties, astronomers were able to conclude that 3I Atlas was probably small compared to Borisov and perhaps even ʻOumuamua. Its faintness implied that it was not a large object. Estimates suggested a size of only a few dozen meters to perhaps a few hundred meters across, depending on assumptions about its surface reflectivity. If it was dark and carbon-rich, it could have been on the larger end of that scale. If it was more reflective, it could have been smaller. This range was frustratingly broad, but it was the best that observations could allow. Compare this to one ʻOumuamua, which was estimated to be between 100 and 400 meters long, though with its own set of uncertainties due to its unusual shape and brightness variations. 2I Borisov, by contrast, was clearly larger, with its nucleus estimated to be several kilometers across, comparable to typical solar system comets. In this spectrum, 3I Atlas likely falls closer to the ʻOumuamua side, small, faint, and hard to detect. Its diminutive size may help explain why it was discovered so late in its passage and why it vanished so quickly from view. One of the difficulties in measuring 3I Atlas's size also came from the fact that astronomers had so little time to track it. Observations spanned only a short period, and with faint objects, the longer they are tracked, the better the models become. With more time, subtle changes in brightness could have revealed whether it was tumbling, whether it had outgassing jets like a comet, or whether its brightness was influenced by shape. But in the case of 3I Atlas, the data simply wasn't there. That meant size estimates had to remain broad guesses rather than precise calculations. Another complication comes from the possibility of non-gravitational forces, such as outgassing. For comets, the release of gas and dust as ices sublimate can create jets that push the object slightly, altering its orbit. In principle, careful measurements of these tiny deviations can give hints about the size and mass of the nucleus. But 3I Atlas was too faint and too short-lived to allow such measurements. Astronomers couldn't detect any obvious outgassing, which left one less tool to constrain its size. In some ways, this difficulty is part of the larger pattern with 3I Atlas. Unlike Borisov, which was cooperative and bright, or ʻOumuamua, which was bizarre but at least studied extensively for weeks, Atlas gave astronomers almost nothing to work with. It was faint, small, and racing through the sky on a trajectory that allowed little time for detailed study. As a result, its size remains one of the many open mysteries about it. But even with the uncertainty, the small size estimate carries an important implication. It suggests that interstellar objects may come in a wide variety of sizes, including some so small that they could easily escape detection unless surveys happen to be watching the right patch of sky at the right time. If 3I Atlas was indeed only a few dozen meters across, it's a reminder that for every interstellar visitor we detect, there may be countless others slipping past unseen. There is also a sobering lesson here. The smaller the object, the less we can learn about it, even if it carries the same interstellar significance. While a giant interstellar comet like Borisov can yield chemical compositions, dust emissions, and activity patterns, something like Atlas leaves only a whisper in the data. Its size is not just a curiosity, it's directly tied to how much knowledge we can extract. So, in the end, astronomers had to settle for broad guesses about the dimensions of 3I Atlas, likely placing it in the small to mid-size range of interstellar objects. Its faintness suggested something not grand or spectacular, but rather modest, an inconspicuous shard of rock or ice that happened to wander into our view before fading back into the darkness. The difficulty in measuring its size highlights the challenges we face in studying these visitors. They don't wait for us, and unless they are large and bright, they slip away with most of their secrets intact. When astronomers talk about the brightness of an object like 3I Atlas, they are really talking about two different but related measurements. One is its apparent magnitude, which is how bright it looks from Earth through a telescope. The other is its absolute magnitude, which is how bright it would appear if placed at a standard distance. Together, these values help researchers estimate not only how easy it is to observe but also what it might be made of and how large it could be. In the case of 3I Atlas, brightness turned out to be one of its most defining features, because it was astonishingly faint compared to its predecessors. To put this in perspective, let's compare it to the earlier interstellar visitors. When ʻOumuamua was first detected in 2017, it had an apparent brightness around 20th magnitude and faded steadily after discovery. That was faint, but still bright. Enough for powerful observatories like Pan-STARRS and the Very Large Telescope to follow it for weeks. By contrast, Borisov, the second interstellar object, was much more cooperative. At its brightest, it reached around 15th magnitude, making it possible not only for large professional observatories to study it but also for dedicated amateur astronomers with moderately sized telescopes to catch a glimpse. 3I Atlas, however, never reached such brightness. At the time of its discovery in December 2019, its apparent magnitude was estimated around 19th or 20th, placing it in the range where only large professional telescopes could reliably study it. Unlike Borisov, which flared up thanks to its active cometary outgassing, Atlas showed no significant activity that could have brightened it. It remained faint and elusive throughout its brief observational window. This faintness had enormous consequences for how the scientific community could engage with it. For most amateur astronomers, even those with advanced backyard equipment, 3I Atlas was simply out of reach. Observing something at 19th or 20th magnitude typically requires telescopes with wide apertures, often in the range of 1 meter or more, coupled with long exposure times and sensitive imaging cameras. That's far beyond what hobbyists typically have access to, meaning this interstellar visitor remained invisible to nearly everyone outside the professional community. Even professional astronomers found it challenging. Observing a faint, fast-moving target requires careful coordination. The object is not only dim but also racing across the sky, meaning telescopes have to track it with extreme precision. If the telescope doesn't keep up, the light smears into streaks during long exposures, and the signal-to-noise ratio drops further. With Atlas, this meant that every moment of observation was a struggle against faintness and motion. Why was it so faint compared to Borisov or even ʻOumuamua? The most straightforward explanation is size. A smaller object naturally reflects less light. If 3I Atlas was indeed only tens to a few hundred meters across, its brightness would be inherently limited. Another factor is surface composition. A dark, carbon-rich surface absorbs more sunlight and reflects less, further reducing brightness. Lastly, a lack of cometary activity meant it did not have a glowing coma or tail to boost its visibility, unlike Borisov, which released clouds of dust and gas that expanded its apparent brightness. The faintness also complicated estimates of its absolute magnitude. Astronomers suggested values around h equals 16 to 18, but with large uncertainties. For comparison, ʻOumuamua's absolute magnitude was closer to 22, but its unusual reflective properties and elongated shape made it stand out more dramatically. Borisov's absolute magnitude, by contrast, was lower, meaning it was brighter, consistent with its much larger nucleus. Atlas's range put it squarely in the category of a small, dark visitor, something that was never going to put on a celestial show for the public. For the general public, this was one of the reasons 3I Atlas did not capture the same level of fascination that ʻOumuamua did. There were no dramatic artist's impressions of a strange, tumbling shard. There was no cometary display visible even to small observatories. There was, simply put, almost nothing to see. For an interstellar visitor, Atlas was quiet, subtle, and secretive, flashing through our skies without spectacle. And yet, the faintness of 3I Atlas is itself a profound clue. It suggests that many interstellar objects passing through our solar system might look exactly like this: small, dark, and nearly invisible unless our surveys are extraordinarily lucky. If Atlas had not been caught by the automated telescopes of the Atlas survey, it might never have been detected at all. That raises the tantalizing possibility that countless similar objects slip past Earth every year, their faint trails unnoticed in the vastness of the sky. So, while 3I Atlas may have been invisible to amateur astronomers and even difficult for professionals, its faintness told us something important. Interstellar visitors come in all flavors, and not every one will be dramatic. Some, like Borisov, will flare up with cometary activity, bright enough to be admired by humans on Earth. Others, like Atlas, will remain shadows at the edge of detectability, reminding us that our view of the universe is still limited by the sensitivity of our instruments. When it comes to the material composition of 3I Atlas, we run into one of the greatest challenges of studying interstellar visitors. We simply do not get enough light from them to perform the kinds of detailed spectroscopic analyses that would allow us to identify their exact makeup. In astronomy, the fingerprints of elements and compounds come from spectra, the way light is absorbed or emitted at certain wavelengths. For an object as faint as Atlas, gathering such data is extremely difficult, and in this case, the window of opportunity closed almost as soon as it opened. That said, scientists are not entirely in the dark. They can infer possibilities by comparing Atlas's brightness, lack of cometary activity, and behavior to what we know from solar system objects and the two earlier interstellar visitors. The first clue comes from brightness and reflectivity. As discussed earlier, Atlas was faint, suggesting that it was small, dark, or both. Objects with low albedo, reflectivity, are often rich in carbon and other dark, organic compounds. In the outer regions of our own solar system, many comets and asteroids have such surfaces, coated in tar-like substances that form after billions of years of exposure to cosmic rays. If Atlas had a similar surface, that would explain its low reflectivity and faintness. On the other hand, if it was made of lighter, icier material, it might still appear faint simply because of its small size. The second clue comes from activity, or the lack of it. Comets are typically rich in volatile ices, such as water, carbon dioxide, and carbon monoxide. When they approach the Sun, these ices sublimate, releasing gas and dust that form a coma and tail, which dramatically increase brightness. Borisov was a textbook example of this, clearly active and displaying behavior consistent with icy bodies in our solar system. Atlas, however, showed little to no detectable activity. That suggests one of two possibilities. Either it lacked volatile ices altogether, or it had a crust or insulating surface layer that prevented sublimation. If it lacked ices, then Atlas may have been more asteroid-like, essentially a rocky body ejected from its home system, perhaps from the inner regions near its parent star. That would make it fundamentally different from Borisov and more similar to ʻOumuamua, which also showed no traditional cometary activity. On the other hand, it's possible that Atlas did have ices, but they were buried beneath a protective mantle of rock or organic-rich material that shielded them from solar heating. If that was the case, Atlas might have been an inactive or dead comet, an object that once had volatile activity but had since exhausted or sealed off its supply. The third line of reasoning comes from behavior and orbit. Atlas followed a clean hyperbolic trajectory, with no noticeable deviations from outgassing. When ʻOumuamua was studied, small deviations from its predicted orbit sparked intense debate. Some attributed it to outgassing, while others suggested alternative explanations, including unusual physical properties. Atlas, by contrast, showed no such anomalies, further supporting the idea that it was inert and inactive during its passage. Another interesting theory concerns the possibility of organic-rich surfaces. In the galaxy, it's expected that many interstellar objects accumulate carbon compounds and tholins, complex organic molecules formed by radiation processing of simpler materials. These compounds can make a surface very dark and red in color. In fact, ʻOumuamua itself appeared reddish in spectral measurements, consistent with such tholin-coated surfaces. Atlas may have shared a similar composition, though direct spectral confirmation was never obtained due to its faintness. There's also speculation about whether interstellar objects like Atlas could represent a broader diversity of material than what we find in our solar system. Planetary systems elsewhere may produce rocky shards with different mineral compositions, icy bodies with exotic volatiles not common here, or hybrid objects that blur the boundaries. Since Atlas was so faint, we cannot directly test these possibilities, but its very existence reminds us that the galaxy likely produces far more variety than we have yet sampled. Ultimately, what astronomers think about Atlas's material composition is framed by comparison. Compared to Borisov, it looked less like an active comet and more like a rocky or dormant body. Compared to ʻOumuamua, it shared the trait of inactivity, though ʻOumuamua at least left behind intriguing anomalies in brightness and trajectory that sparked endless debate. Atlas, by contrast, slipped by quietly, almost as if it wanted to keep its secrets. This makes 3I Atlas both frustrating and fascinating. Frustrating, because without spectra or extended monitoring, we will never know exactly what it was made of. Fascinating, because its faintness and inactivity suggest that the diversity of interstellar visitors is larger than we first imagined. Not every interstellar object will be bright and active. Some will be inert, small, and quiet, carrying within them the hidden materials of distant stars but never offering us a clear look. So, in theory, scientists think Atlas was either a rocky, asteroid-like shard from another star system or a dormant, carbon-rich cometary body with exhausted volatiles. Either way, it represents a sample of material forged far beyond our solar system, a silent traveler whose true composition we may never pin down with certainty. But even in its silence, it speaks to the incredible variety of building blocks that exist across the galaxy. The question of why 3I Atlas was so faint compared to the first two interstellar objects is one of the most important aspects of its story, because faintness is not just an observational inconvenience, it's a clue about the physical nature of the object itself. ʻOumuamua and Borisov both gave astronomers at least something substantial to work with. ʻOumuamua was strange and dim, but it reflected light in a way that allowed us to track its brightness variations. Borisov, being an active comet, released material that made it much brighter and easier to analyze. 3I Atlas, however, was so faint that even professionals struggled to gather enough data. This faintness is precisely why it remains the most mysterious of the interstellar visitors detected so far. One major reason for its faintness is likely its small size. Brightness is closely tied to the surface area of an object. The larger it is, the more sunlight it reflects back toward us. Estimates for 3I Atlas place it in the range of just a few dozen to perhaps a few hundred meters across. By contrast, Borisov's nucleus was estimated at nearly a kilometer in diameter, which made it naturally brighter. ʻOumuamua was also thought to be on the order of 100 to 200 meters long, but its unusual shape and reflective properties made it appear slightly more noticeable. If Atlas was closer to the lower end of size estimates, then it simply didn't have much surface area to reflect light, making it inherently dim. Another factor is surface reflectivity, also known as albedo. Objects coated with dark materials like carbon compounds reflect very little sunlight. Many outer solar system bodies, such as comets and Kuiper belt objects, have albedos of only a few percent, essentially as dark as charcoal. If Atlas had such a surface, then even if it wasn't unusually small, it still would have appeared faint. ʻOumuamua, while not extremely bright, had a surface with enough reflectivity that astronomers could track its brightness changes and infer its elongated shape. Borisov, meanwhile, grew brighter because sunlight caused volatile ices to sublimate, releasing reflective dust and gas that surrounded the nucleus. Atlas had no such boost. The absence of cometary activity is another key reason. Borisov's activity was what made it a spectacular object to study. It shed gas and dust, forming a bright coma and tail that dramatically increased its visibility. Atlas, on the other hand, appeared inert. If it was once icy, those ices may have already been depleted, or they may have been buried under thick crust that prevented sublimation. Without a coma or tail, Atlas looked more like a dark, inactive rock. And without that brightening effect, it remained a faint point of light, hard to track even with large telescopes. On top of its physical faintness, there's the issue of its timing and geometry of observation. When astronomers discovered Atlas, it was already on its way out of the solar system. That meant it was getting farther from both Earth and the Sun, making it dimmer each passing day. ʻOumuamua, by contrast, was discovered relatively soon after its perihelion, its closest approach to the Sun, meaning it was still bright enough to study for weeks. Borisov was discovered months before perihelion, allowing astronomers to prepare for and capture its brightest phase. Atlas never offered that luxury. It was found late, already faint, and only grew dimmer. Another reason it was harder to study was its speed and trajectory. Like all interstellar objects, Atlas followed a hyperbolic path, moving rapidly across the sky. For faint objects, this creates a huge challenge. To detect something so dim, astronomers often use long exposure times, letting light build up in their detectors. But with Atlas moving so fast, long exposures risked smearing the object into a streak, making it harder to distinguish from background noise. Observers had to carefully track its path with high precision, and even then, the signal-to-noise ratio was low. The faintness also magnified data limitations. With only a handful of good observations, astronomers struggled to pin down its orbit with high accuracy. Unlike ʻOumuamua, which could be studied for weeks, or Borisov, which was observed for months, Atlas was essentially a blink-and-you'll-miss-it event. Many research teams didn't even have time to train their instruments on it before it became too dim to observe. That meant there was no chance to gather spectra, no time for detailed brightness measurements, and no way to study its rotation, shape, or surface color with confidence. In short, Atlas was faint because of a combination of intrinsic and extrinsic factors. Intrinsic factors, it was probably small, dark, and inactive. Extrinsic factors, it was discovered late, far from the Sun, and fading quickly. Compared to ʻOumuamua, which sparked global excitement, or Borisov, which offered months of study, Atlas was simply too faint to make an impression beyond professional circles. For the public, that made it almost invisible. No photos, no artistic renderings that matched reality, no chance to see it through even the most advanced amateur telescopes. For scientists, though, its faintness carried its own message. Not every interstellar visitor will be spectacular. In fact, the majority may be more like Atlas, small, dark, and barely detectable, slipping through our skies silently. This is why Atlas is often described as the most elusive interstellar object yet. It forced astronomers to confront the reality that the vast majority of such visitors will never be noticed at all. Our surveys must catch them at just the right place and time, and even then, we may only get a fleeting, faint glimpse before they vanish forever. One of the most defining aspects of 3I Atlas, and the reason it remains shrouded in mystery, is the severe limitation of data that astronomers were able to gather during its brief appearance. Interstellar objects like ʻOumuamua and Borisov gave the scientific community something rare, a window of time long enough to capture meaningful data about their brightness, composition, and orbital details. But Atlas slipped through almost unnoticed, and by the time its interstellar nature was confirmed, it was already fading into the cosmic dark. This scarcity of information is why Atlas has become more of a tantalizing hint than a fully understood discovery. The most immediate data limitation came from its faintness. Atlas was never a bright object, even at the time of discovery. Unlike Borisov, which flared with cometary activity, Atlas remained inert and dim, offering no helpful coma or tail to amplify its signal. Astronomers depend on brightness for almost everything, determining an object's size, reflectivity, composition, and activity all stem from how much light it reflects or emits. With Atlas reflecting so little sunlight, every piece of information extracted from it came with huge uncertainties. Even basic estimates like its size varied widely because its low albedo made it impossible to know how much of its faintness came from being small versus being dark. Another critical limitation was the short observational window. By the time Atlas was spotted by the Atlas telescope system, it was already heading outward, moving away from both the Sun and Earth. The farther it traveled, the dimmer it became. For astronomers, this meant they only had a few weeks of potentially useful data before the object dropped below detectability thresholds. Compare this with Borisov, which was tracked for many months, or even ʻOumuamua, which was monitored for several weeks under better brightness conditions. Atlas was simply gone before anyone could mobilize a full scientific campaign to study it. This short window meant there was no chance to capture spectroscopic data, which would have been invaluable. Spectroscopy, the analysis of light broken into its component wavelengths, is the main way astronomers identify the materials on or around celestial objects. It's how we know that comets contain water, carbon dioxide, and other volatiles. It's how we detected tholins and organic compounds on the surfaces of Kuiper belt objects. But spectroscopy requires a reasonably bright target. Atlas never provided that. Its faintness and rapid fading meant telescopes couldn't collect enough photons to build a usable spectrum. As a result, we don't know whether it was rocky, icy, or covered in organics. Even photometric data, measurements of its brightness over time, were extremely limited. Photometry can reveal an object's rotation rate, shape, and surface properties. ʻOumuamua's odd, tumbling light curve gave us the first clues that it was elongated or pancake-shaped. Borisov's brightness changes helped confirm it was behaving like a typical comet. With Atlas, the faint signal and short window meant there weren't enough measurements to construct a reliable light curve. Any rotation or shape details remain completely unknown. The lack of data also restricted how precisely astronomers could calculate its orbit. With ʻOumuamua and Borisov, dozens and then hundreds of measurements allowed researchers to pin down their hyperbolic trajectories with high confidence. That level of detail let scientists calculate where they came from and how fast they were traveling. For Atlas, the small number of measurements meant that while its hyperbolic orbit was clear enough to confirm its interstellar origin, the finer details, like tracing its past path back to a possible star system of origin, were beyond reach. Another issue was competition for telescope time. The global astronomy community relies on shared resources, from ground-based telescopes to space observatories. When Borisov was discovered, it became a priority target, with observatories around the world dedicating time to study it because it was bright and scientifically rich. Atlas, being faint and already fading, simply didn't attract the same level of urgency. By the time astronomers realized how little time they had, it was already slipping below the detection threshold of even the largest telescopes. This lack of data also had a ripple effect on public awareness. ʻOumuamua and Borisov captured widespread media coverage in part because scientists had enough information to tell compelling stories about them. ʻOumuamua sparked debates about its unusual shape and possible non-gravitational acceleration. Borisov fascinated people as the first interstellar comet ever observed. Atlas, however, never provided enough concrete details to capture the public imagination in the same way. Its faintness didn't just limit science, it limited cultural impact. In essence, the study of 3I Atlas was constrained by three overlapping limitations: faintness, brevity, and timing. It was too dim to study deeply, visible for too short a time, and discovered too late in its solar system passage for meaningful follow-up. These limitations remind us that interstellar objects are not guaranteed scientific goldmines. Many will pass unnoticed, and even when they are spotted, they may not provide enough light or time to yield answers. But in another way, the scarcity of data also makes Atlas valuable. It highlights the urgent need for faster detection systems, better early warning networks, and more coordinated international response when interstellar visitors are found. When astronomers realized that 3I Atlas was not a bound member of our solar system but an interstellar visitor, the natural next question became, where did it come from? Unlike comets or asteroids born in the sun's gravitational influence, interstellar objects carry with them the fingerprints of entirely different stellar environments. They are pieces of other systems, other stars, other histories. Yet tracing the precise origin of 3I Atlas proved nearly impossible, thanks to its faintness and short observational window. Still, scientists can construct a set of informed theories about where it might have begun its journey, perhaps millions or even billions of years ago. The most direct way to approach this mystery is through its trajectory. When an object enters the solar system on a hyperbolic path, astronomers can calculate its incoming direction and, in theory, rewind its motion backward to see where it came from. With ʻOumuamua, this technique narrowed its approach to somewhere near the direction of the constellation Lyra. For Borisov, its incoming trajectory was traced to a region near Cassiopeia. Both were too imprecise to link to specific star systems, but at least astronomers could define general sky regions. For Atlas, however, the small number of observations made this method much less precise. We know that it came from beyond the sun's sphere of influence, but exactly which stellar neighborhood it once belonged to remains a mystery. Still, we can make some educated guesses. Interstellar objects are believed to originate from planetary system formation. In young star systems, countless planetesimals, small rocky and icy bodies, form in vast numbers. Many of these are perturbed by the gravity of larger planets and are ejected into interstellar space. Over billions of years, these ejected remnants drift between stars until some eventually pass close enough to another star system, like ours, to be briefly captured in a flyby. In this sense, Atlas was almost certainly one of these planetary building blocks, flung out of its birth system long ago. One possibility is that Atlas came from a young, active system where giant planets played a major role in ejecting planetesimals. This is similar to how our own solar system works. Jupiter's immense gravity has likely ejected countless comets into interstellar space. If another star system has a Jupiter-like giant, it could easily sling small icy or rocky objects away at escape velocities. Atlas could very well have been one such casualty, born in the protoplanetary disk of a distant star and cast out before it ever had the chance to grow into something larger. Another possibility is that it originated from the Oort cloud of another star. Just as our Sun has a distant cloud of icy bodies loosely bound at the edge of its gravity, so too do other stars. If a nearby passing star or galactic tide perturbed one of these distant reservoirs, objects like Atlas could be set adrift. Over immense timescales, these bodies drift across interstellar space, becoming wanderers like the one we briefly observed. If Atlas came from such a reservoir, it may have been a frozen remnant from the very edge of a star's planetary system. There's also the intriguing possibility that it came from a binary star system. Binary systems are especially efficient at ejecting planetesimals because their complex gravitational dynamics make stability difficult for small objects. In such systems, one star's tug can destabilize an object orbiting the other, catapulting it into space. If Atlas was born in a binary system, its journey could have begun with such a gravitational slingshot. Even though we cannot name its exact origin, the sheer fact that Atlas made it into our solar system tells us something important about the Milky Way's ecosystem of debris. Objects like Atlas suggest that planetary systems routinely shed material into interstellar space, and those materials drift freely between the stars. Our galaxy is likely filled with countless billions of such objects, each carrying with it the chemistry and history of the system it once called home. Atlas was just one that happened to cross paths with us. It is also worth reflecting on the timescales involved. If Atlas was ejected from its parent system billions of years ago, it may have been wandering the galaxy for nearly the entire history of life on Earth. It could have passed near other stars, drifted through interstellar clouds, or been bombarded by cosmic rays that altered its surface chemistry. By the time it arrived here, it was an ancient traveler, scarred by the environment of deep space. What makes this all the more frustrating for scientists is that with better data, we might have been able to do more than speculate. If Atlas's incoming path had been nailed down with greater precision, it might have been possible to cross-reference its trajectory with nearby stellar motions to see if it plausibly originated from a specific star system. In fact, this is what astronomers attempted with Oumuamua, though even in that case the uncertainties were too high. With Atlas, the faintness and brief observational period left us with far too little. Its birthplace is therefore destined to remain anonymous. And yet, even without pinpointing its exact star system of origin, Atlas teaches us something crucial. Interstellar objects are not one-offs. They are a natural byproduct of planetary system evolution, and their presence in our solar system is a reminder that material constantly flows between the stars. Each interstellar object we detect is not just a visitor. It's proof that planetary formation, ejection, and galactic wandering are universal processes, linking us to star systems we may never see up close. When we think about interstellar objects like 3I Atlas, it's important to remember that their time with us is fleeting. They are not permanent residents of our solar system. They are cosmic travelers, stopping by for only the briefest of encounters before vanishing back into the depths of interstellar space. To understand where 3I Atlas is going, we need to look at its exit trajectory, the hyperbolic path that carried it through our solar system and now leads it away, never to return. Objects bound to the Sun follow closed orbits, ellipses or circles, meaning they are forever trapped by the Sun's gravity. But interstellar objects like Atlas move on hyperbolic orbits, open-ended curves that guarantee a one-way trip. They dive in from the darkness, loop around the Sun under its gravitational influence, and then swing outward again, carrying on into interstellar space. What makes this trajectory special is that it doesn't curve back to close into a loop. Once Atlas passed perihelion, the point of closest approach to the Sun, it began its journey outward, gaining distance from the Sun every day. There is no force strong enough to pull it back into orbit. In the case of Atlas, its orbit was steeply hyperbolic, meaning its excess velocity, the speed it carried even after the Sun's gravity tried to slow it, was far too great for it ever to be captured. This excess speed is what astronomers call its hyperbolic excess velocity, v infinity. For Atlas, that number was high enough to ensure it had already escaped the Sun's grasp the moment it entered. That escape speed is crucial for confirming its interstellar nature, but it also defines its future path, a permanent exit into the galaxy. The exact direction of Atlas's departure can be traced to the constellations of the sky, just as we can for its entry. While the uncertainties in its orbit prevented astronomers from calculating its origin precisely, its outgoing path was somewhat easier to define. After looping around the inner solar system, Atlas departed roughly toward the outer regions of the constellation Pegasus, continuing on a path that would take it further above the galactic plane over time. This doesn't mean it's heading directly toward a nearby star. The distances between stars are so vast that most interstellar objects will wander for eons before approaching another system. Still, by mapping its trajectory, we can at least say where in the sky it is now leaving us. The future of Atlas, then, is one of eternal wandering. With its hyperbolic orbit, it will travel farther and farther from the Sun, first passing beyond the orbit of Neptune, then through the outer reaches of the Kuiper Belt, and finally into the vast emptiness of the Oort cloud. From there, it will break completely free, joining the interstellar medium once again. It may drift for hundreds of millions, even billions of years, until perhaps one day it passes near another star system, repeating the same brief encounter it had with ours. This inevitable exit also highlights the lost opportunities of Atlas. Unlike asteroids or comets bound to the Sun, which astronomers can revisit during future passes, Atlas will never return. Every missed observation window was a permanent loss. Once it faded beyond the reach of telescopes, it was gone forever, and with it the chance to learn more about its size, composition, and behavior. It's a reminder of how fleeting these cosmic encounters are. Scientists must act quickly when interstellar objects are discovered, because they will not wait for us. Interestingly, its departure also sparks some speculation about interstellar pathways. Astronomers often discuss how interstellar objects might serve as natural probes, carrying with them the chemical signatures of their birthplaces. By studying where they come from and where they go, we can begin to map the invisible exchanges of material that occur between stellar systems. Though we lost the chance to study Atlas in detail, we at least know that it is now part of that galactic current of material, one traveler among countless others, drifting endlessly between the stars. For us on Earth, the departure of Atlas marks the end of a brief chapter. From our perspective, it appeared suddenly, was recognized as extraordinary only after precious time was lost, and then quietly faded back into the void. Now it is on its way outward, on a one-way journey beyond our reach, becoming fainter and fainter until even the largest telescopes can no longer track it. If ʻOumuamua was like a mysterious guest who left behind puzzling evidence of their visit, and Borisov was a cometary traveler who revealed much about their nature, Atlas was more like a shadow passing by, a visitor we glimpsed only faintly before it disappeared. And so, where is it going? The answer is both simple and profound: away from us, forever. It is heading back into interstellar space, destined to spend eternity in the vast reaches of the galaxy, carrying with it the secrets of its birth system, secrets we were unable to uncover. Perhaps, in a distant future, another civilization circling another star will spot Atlas as it drifts through their skies, just as we did. For them, it may be another fleeting mystery, or perhaps by then, they'll have the tools to intercept it and learn what we could not. The importance of interstellar objects like 3I Atlas cannot be overstated. On the surface, they may appear to be just small chunks of rock or ice drifting through space, but when we look deeper, they represent something much bigger. They are direct physical samples from other star systems. Unlike the light we collect from distant stars or the spectra of exoplanet atmospheres, interstellar objects are tangible pieces of matter that formed under alien conditions and then made their way to us. Studying them, even briefly, is like holding a fragment of another world in our hands. This is why 3I Atlas matters. Every interstellar object offers us a unique opportunity to learn about the processes of planetary formation beyond our solar system. We know a lot about how planets, comets, and asteroids formed around our own sun, but the galaxy is filled with stars that may have very different environments. The material that gets ejected from those systems carries the chemical fingerprints of their origins. By examining an interstellar object's brightness, composition, and activity, scientists can infer whether it is icy, rocky, metallic, or a mix, and these inferences tell us what building blocks other star systems had available. Another reason these objects are so valuable is that they provide ground truth to complement exoplanet studies. When astronomers look at distant exoplanets, they often rely on indirect methods like transit dips or radial velocity curves, which only give broad strokes. Interstellar objects, by contrast, are literally pieces of those same kinds of systems drifting through space. They provide physical confirmation of what exoplanet observations suggest. For instance, if many interstellar objects appear to be icy, it would confirm that other systems produce comet-like debris similar to our own Oort cloud. If some are rocky, that indicates those systems may eject fragments of inner planets or asteroids. They also matter because they help answer the question of how common ejection really is. Our models suggest that young star systems eject massive amounts of material during their early chaotic years. However, until we began finding interstellar objects, this was only theoretical. Now, with ʻOumuamua, Borisov, and Atlas, we have confirmation that ejected debris not only exists but is plentiful enough that our telescopes can detect them in real time. Each discovery strengthens the case that interstellar debris is constantly moving between stars. This has huge implications for galactic dynamics and even astrobiology. Speaking of astrobiology, one of the most profound reasons interstellar objects matter is their potential role in the transfer of life's ingredients between star systems. This idea, known as panspermia, suggests that the raw materials for life, or even microbial life itself, could hitch a ride on such objects and spread across the galaxy. While the odds of that happening are debated, the mere presence of icy, organic-rich objects drifting between stars supports the possibility that at least the chemical precursors of life could be distributed widely. Studying 3I Atlas, even in limited detail, contributes to this ongoing discussion of whether life seeds are scattered throughout the Milky Way. There's also a more practical, future-oriented reason these visitors matter. They represent targets for exploration. Right now, our spacecraft are limited to exploring local solar system bodies, but interstellar objects could one day be studied up close by missions specifically designed to intercept them. If humanity hopes to understand the galaxy in greater depth, sending probes to such objects may be one of the few affordable and achievable ways to get material directly from another star system. Every detection we make now helps us prepare for those missions by teaching us about their speeds, sizes, and trajectories. But perhaps the biggest reason Atlas matters is what it symbolizes. It shows us that our solar system is not isolated. It is connected to a galactic community. Pieces of other systems find their way here, and by studying them, we connect our story to the stories of countless other stars. Even though Atlas itself was faint, fleeting, and frustratingly elusive, its presence was another reminder that we live in a galaxy of exchange, migration, and cosmic dialogue. Ultimately, the value of Atlas is not just in what we learned about it, but in what it represents, the beginning of a new era in astronomy. Until recently, interstellar objects were purely theoretical. Now, in just a handful of years, we've detected 3. Each one tells us that these visitors are not miracles of chance. They are expected, frequent, and meaningful. By catching them and studying them, we are opening a new frontier of discovery, one that takes us beyond our solar system without ever leaving home. Studying interstellar objects like 3I Atlas may sound straightforward in theory. You spot one in the sky, point telescopes at it, and gather as much data as possible. But in practice, it's one of the most difficult tasks modern astronomy faces. The challenges lie not just in their rarity, but in the nature of these objects themselves. They are faint, fast-moving, and unforgivingly brief visitors. Astronomers have to work against the clock, against the limits of technology, and against the immense distances involved. One of the first and most obvious difficulties is their faintness. Even the brightest comets within our solar system can sometimes only be seen with binoculars or telescopes. Interstellar objects, on the other hand, rarely get close enough to the Sun to ignite the kind of spectacular outbursts that make comets visible to the naked eye. 3I Atlas was particularly faint, hovering near the detection threshold of the Atlas survey and fading quickly as it moved away. This means astronomers couldn't collect much detailed information. There was barely enough light for basic measurements, let alone high-resolution spectroscopy. A faint object gives very little signal, and when you're looking at something across tens of millions of kilometers, every photon counts. Adding to this, interstellar objects are moving extraordinarily fast. Unlike comets and asteroids bound to the Sun, which orbit at predictable speeds and return periodically, interstellar visitors zip through the solar system at breakneck velocities, tens of kilometers per second relative to the Sun. That might sound manageable, but in astronomical terms, it's like trying to photograph a speeding bullet from thousands of miles away. The speed means they pass quickly through the inner solar system, the region where our telescopes can best observe them. ʻOumuamua, for example, was discovered after its closest approach to Earth had already occurred, and Atlas followed a similar pattern. By the time astronomers knew what they were looking at, the window of opportunity was already closing. Another challenge is time. With objects like long-period comets, astronomers sometimes get months or even years to track them as they approach the Sun. But interstellar objects don't afford that luxury. 3I Atlas was observable for only a brief stretch of time before it grew too faint to study. This compressed timeline forces astronomers to scramble. They must coordinate multiple observatories around the globe, request emergency observing time on major telescopes, and prioritize which data to gather, all while knowing that if they miss the chance, the object is gone forever. There are no second chances with interstellar visitors. Compounding this is the problem of instrument sensitivity. Even our best telescopes have limits to what they can detect. Many interstellar objects are probably passing through the solar system right now, but they are simply too small or faint for us to see. 3I Atlas pushed right up against these limits, being difficult to track even with large observatories. This means that in many cases, astronomers are forced to make do with incomplete or noisy data, which leaves huge uncertainties in things like size, shape, and composition. There's also the issue of trajectory uncertainty. When an object is detected late, astronomers only have a handful of observations to work with. The fewer the data points, the harder it is to calculate a precise orbit. With Atlas, this meant that although its hyperbolic path was clear, smaller details, like exactly where it came from or where it was going, remained ambiguous. These gaps make it more difficult to connect the object to potential origin systems or compare it cleanly to solar system bodies. The difficulty isn't just technical, it's also logistical. Large telescopes like those at Mauna Kea, Keck, or the Very Large Telescope in Chile are in high demand. Observing time is scheduled months in advance, and astronomers must usually apply for it through competitive proposals. When something unexpected like an interstellar object shows up, they have to file urgent requests, hoping their peers and review boards agree that this rare visitor deserves immediate attention. Sometimes, by the time observing time is secured, the object has already faded away. Atlas was a prime example of this problem. Its brief visibility meant that many top-tier facilities missed the chance to examine it in detail. These challenges underscore a frustrating truth. We know interstellar objects are scientifically priceless, but we are often ill-equipped to study them in the moment. Unlike planets, moons, or even regular comets, which can be studied over and over again, interstellar visitors demand precision, coordination, and a bit of luck. Without all three, the opportunity slips away. But perhaps the greatest challenge is psychological. These fleeting encounters remind us just how much of the universe we're missing. For every Atlas, there are likely dozens, perhaps hundreds, of other interstellar travelers that passed unnoticed through our skies, too faint for our current instruments. Astronomers know these opportunities exist, but until new technologies like the Vera C. Rubin Observatory come online, they are forced to accept that most of these visitors will pass unstudied. In the case of 3I Atlas, its faintness, speed, and short window of observation combined into a perfect storm of difficulty. What should have been an extraordinary opportunity to study a messenger from another star system instead became a cautionary tale of how unprepared we still are to take full advantage of such discoveries. It wasn't that scientists weren't eager, it was simply that the object gave them almost nothing to work with. In that sense, Atlas serves as both a frustration and a motivator. It reminds us of the gaps in our current capabilities while pushing us toward better readiness for the next encounter. The discovery of 3I Atlas, like that of ʻOumuamua and Borisov before it, was only possible because of the extraordinary technological advancements in sky surveys over the last 2 decades. For most of human history, astronomy relied on painstaking visual observation. Even in the photographic era, astronomers would compare glass plates manually to look for moving objects among the stars. That method, while revolutionary in its time, was simply too slow and too limited to catch something as fleeting as an interstellar visitor. It was only with the development of automated digital surveys, telescopes designed to scan vast portions of the sky night after night, that we gained the capability to detect these short-lived cosmic travelers. One of the most important systems in this regard is the Asteroid Terrestrial Impact Last Alert System, ATLAS, which, as the name implies, was built to look for asteroids on paths that might collide with Earth. Its design focuses on monitoring the entire visible sky, every night, to spot faint moving objects before they get too close. The beauty of Atlas lies in its efficiency rather than its size. Its telescopes are modest compared to the giants of the astronomical world, with mirrors only about 0.5 meters in diameter. But they make up for this by sweeping huge swaths of sky at once and automatically processing the data with sophisticated algorithms that flag moving objects. This wide coverage is exactly what's needed to catch rare, fast-moving visitors like 3I Atlas. Alongside Atlas, another key player is PanSTARRS, Panoramic Survey Telescope and Rapid Response System, located in Hawaii. PanSTARRS has already made history as the survey responsible for discovering 1I ʻOumuamua, the very first interstellar object ever observed. Unlike Atlas, PanSTARRS uses larger 1.8-meter telescopes equipped with incredibly powerful digital cameras, capable of capturing images of faint objects across enormous fields of view. It's essentially designed to find anything that moves, whether that's an asteroid, a comet, or an interstellar traveler. Its ability to detect faint objects at great distances makes it particularly useful for catching unusual trajectories, which often turn out to be the signatures of hyperbolic interstellar paths. These systems work together with a global network of observatories. When a survey like ATLAS or PAN-STARRS flags a potential object, follow-up is critical. Other facilities, such as the Catalina Sky Survey in Arizona or the Zwicky Transient Facility, ZTF, in California, often jump in to confirm the detection and refine orbital data. The ZTF, in particular, is another modern marvel. Its 48-inch Samuel Oskin telescope at Palomar Observatory is fitted with one of the largest digital cameras in the world, enabling it to capture detailed images of the sky at high speed. Its wide field of view and rapid response capabilities make it an ideal complement to ATLAS and PAN-STARRS. What ties all these systems together is not just their optics, but the computational infrastructure behind them. Detecting something like 3i ATLAS is a needle in a haystack problem. Each night, surveys collect terabytes of data, filled with millions of stars and galaxies. The moving objects are tiny points of light shifting slightly from one night to the next. Without advanced algorithms to compare images, identify moving sources, and distinguish them from noise or false positives, spotting a faint interstellar visitor would be impossible. Machine learning and automated detection pipelines now play a central role in filtering this ocean of data. ATLAS, PAN-STARRS, and ZTF are essentially a marriage of optics and artificial intelligence. Without both, the discovery of interstellar objects would remain beyond reach. Another important aspect of these surveys is their international collaboration. No single telescope can monitor the sky at all times. By having a distributed system of surveys around the world, astronomers ensure that detections can be confirmed, tracked, and studied even as the Earth rotates. Once 3i ATLAS was flagged by ATLAS, observatories across the globe worked together to collect additional data, pooling resources to maximize what could be learned before the object faded. This rapid response teamwork has become a hallmark of modern astronomy, and it's one of the reasons we've been able to identify multiple interstellar visitors within just a few years. It's worth emphasizing that these surveys weren't originally designed to find interstellar objects at all. Their primary mission is planetary defense, scanning for asteroids that could pose a threat to Earth. But in doing this, they also create the conditions necessary to detect extremely rare phenomena. In many ways, the discovery of 3i ATLAS was a happy accident, a bonus outcome of systems already in place for entirely different reasons. Yet this overlap highlights a key point. The tools we develop for one purpose often open doors to discoveries we never expected. The importance of these surveys will only grow in the future. ATLAS has already expanded to include additional telescopes in Hawaii and Chile, giving it better coverage of the southern hemisphere sky. PAN-STARRS is planning upgrades to increase sensitivity, and new surveys are on the horizon, such as the Vera C. Rubin Observatory, which will revolutionize our ability to find faint, fast-moving objects. The story of ATLAS and other surveys shows us that without these automated skywatchers, we might still believe that interstellar objects were purely theoretical. Now, thanks to technology, we know they are not only real but also passing through our solar system far more often than we once thought. In the end, the discovery of 3i ATLAS was not the result of luck alone. It was the result of decades of investment in wide-field digital surveys, advanced computational tools, and a global network of astronomers ready to leap into action. It reminds us that in the vastness of the universe, preparation is everything. Without these technological marvels, ATLAS would have slipped past unnoticed, just another silent wanderer lost in the night. The limitations of current surveys like ATLAS and PAN-STARRS, while remarkable in what they have achieved, highlight a simple truth. We are only scratching the surface of what's out there. For every 1i ʻOumuamua, 2i Borisov, and 3i ATLAS that we've detected, there are likely dozens, maybe even hundreds, of interstellar objects passing through the solar system unnoticed, too faint or too fleeting for our present systems to catch. This is where the Vera C. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, LSST, comes into the picture. When it begins full operations, expected in the near future, it will transform our ability to detect rare cosmic travelers and could usher in a golden age of interstellar discoveries. The Rubin Observatory is not just another telescope, it is a revolutionary leap in survey astronomy. Located on Cerro Passion in Chile, at an elevation of over 2,600 meters, it is built to take advantage of some of the clearest skies on Earth. Its primary mirror is 8.4 meters in diameter, making it one of the largest survey telescopes ever constructed. But its true power comes not only from its size, but from its unique design. It pairs this massive mirror with an unprecedentedly wide field of view, 3.5 degrees across, large enough to cover 40 times the apparent size of the full moon in a single exposure. The heart of the Rubin Observatory is its 3.2 gigapixel camera, the largest digital camera ever built for astronomy. Each image it takes will be absolutely enormous, so large that it would take hundreds of ultra-high-definition televisions to display a single photograph at full resolution. With this camera, Rubin will scan the entire southern sky every 3 nights, building an ever-evolving time-lapse movie of the heavens. This rapid cadence is what sets Rubin apart. By repeatedly imaging the whole sky so quickly, it can track changes in brightness and movement that would otherwise go unnoticed. For interstellar objects, this capability is a game-changer. Rubin's sensitivity means it will be able to detect objects that are much fainter than those caught by Atlas or Pan-STARRS. Estimates suggest that while Atlas and Pan-STARRS can only reliably catch interstellar visitors as they come relatively close, Rubin will be able to see them from much farther away, giving astronomers more time to organize follow-up observations. This longer lead time is critical. With ʻOumuamua and Atlas, by the time scientists realized what they were looking at, the objects were already receding. Rubin could provide weeks or even months of advance warning, enough to mount coordinated studies and perhaps even consider rapid spacecraft missions to intercept. Rubin will also excel at identifying unusual orbits. Most asteroids and comets follow paths dictated by the Sun's gravity, making their movements predictable and relatively uniform. Interstellar objects, by contrast, follow hyperbolic trajectories that stand out as outliers. Because Rubin will generate such a massive dataset, tens of terabytes of data every night, it will have the statistical power to spot these rare anomalies quickly. Automated pipelines will comb through the data in real time, flagging unusual candidates for immediate follow-up. The moment a potential interstellar visitor is detected, the global astronomy community can be alerted almost instantly. Another reason Rubin is so promising is its role in contextualizing interstellar visitors. Every detection adds to the growing population of known interstellar objects, and with Rubin's help, that population could grow significantly. Some estimates suggest Rubin might find 1 or 2 new interstellar objects every year, a staggering improvement over the current pace of discovery. This would allow astronomers to go beyond treating each visitor as a unique curiosity and begin studying them as a statistical population. Are most of them comet-like Borisov, or elongated and unusual, like ʻOumuamua? Are their speeds and trajectories consistent with being ejected from planetary systems like our own, or do some come from entirely different galactic environments? With Rubin, these questions could move from speculation to data-driven science. The observatory will also strengthen planetary defense efforts, since its primary mission includes cataloging potentially hazardous asteroids. This dual role, protecting Earth while simultaneously expanding our cosmic horizons, is part of what makes Rubin such a landmark project. It ensures that the enormous investment in building and operating the facility pays dividends across multiple fields of astronomy. Of course, Rubin's promise also depends on infrastructure to handle its colossal data output. Each night, it will generate more data than most telescopes collect in years. Managing this requires advanced computational pipelines, artificial intelligence, and international collaboration to sift through the flood of information. But this challenge is also an opportunity. The very tools that will identify near-Earth asteroids will simultaneously flag the rare interstellar visitor, making Rubin a sort of cosmic multitasker. When it comes online, the Vera C. Rubin Observatory will not just improve our chances of finding interstellar objects, it will fundamentally redefine them. No longer will these visitors be once-in-a-generation surprises. Instead, they could become regular additions to our catalogue, each one carrying clues about distant planetary systems and the broader galactic environment. For the first time, we might begin to see interstellar objects not as anomalies but as part of the cosmic landscape, passing through our solar system with a frequency we are finally able to perceive. For 3I Atlas, Rubin arrives too late to help. But its discovery, faint and fleeting as it was, serves as a proof of concept for why Rubin matters. Each missed opportunity underscores the need for more powerful surveys, and Rubin stands ready to deliver. When the next interstellar traveler comes, and it surely will, Rubin may be the first to greet it, transforming what was once a frustratingly brief encounter into a fully realized scientific event. When ʻOumuamua passed through our solar system in 2017, scientists were left both exhilarated and frustrated. Exhilarated because it was the first confirmed interstellar visitor, but frustrated because by the time we realized what it was, the object was already racing away at nearly 90,000 kilometers per hour, far beyond our reach. The same story played out with 2I Borisov in 2019, and again with 3I Atlas. Each time, astronomers gathered as much data as they could, but none of these encounters allowed for direct, up-close investigation. This has sparked a growing movement in the scientific community. The idea of preparing spacecraft missions capable of intercepting interstellar objects when they appear, or even pursuing them long after they've left. The concept isn't entirely new. In fact, in the wake of ʻOumuamua's discovery, several proposals emerged under the umbrella of interstellar interceptor missions. The most famous of these was Project Lyra, a concept study initiated by the Initiative for Interstellar Studies, I4IS. Project Lyra asked the question, could we design a spacecraft capable of chasing down ʻOumuamua, even years after its departure? The answer was a tentative yes, but with enormous challenges. The mission would require highly advanced propulsion, possibly using solar sails, nuclear propulsion, or even gravitational assists around giant planets to slingshot the craft to extraordinary speeds. While technically possible in theory, such a mission would require a level of urgency and funding that was impractical by the time ʻOumuamua had already faded from view. But the idea didn't die. Instead, it evolved. Scientists realized that instead of scrambling to launch a mission after the fact, we could prepare in advance. One proposal is to build a ready-to-launch interstellar interceptor, a spacecraft kept on standby in orbit or at a stable location like the Earth-Sun Lagrange points. Once a promising interstellar visitor is detected, something that future surveys like the Vera Rubin Observatory will be far more capable of spotting with early notice, the interceptor could be deployed on short notice to adjust its trajectory and intercept the object while it is still within reach. This proactive approach could transform fleeting glimpses into groundbreaking close-up encounters. Another innovative idea involves modular spacecraft swarms. Instead of relying on a single large spacecraft, a fleet of small, inexpensive probes could be launched in different directions whenever a new object is discovered. These probes, using solar electric propulsion or compact chemical systems, could adjust their paths to target the interstellar visitor. Even if only a handful succeed in reaching the target, they could return invaluable data, including high-resolution images, spectroscopic analysis of surface composition, and perhaps even in-situ measurements of dust or gas released by the object. NASA has also begun seriously considering this possibility. In 2022, the agency funded early-stage research into a mission concept called the Interstellar Object Explorer, IOE. This idea builds on the lessons of previous comet intercept missions, like ESA's Rosetta mission to Comet 67P and NASA's Deep Impact mission. The Interstellar Object Explorer would be designed for agility, able to adjust its trajectory quickly after launch to target a newly discovered object. Its scientific payload could include cameras, spectrometers, dust analyzers, and possibly even a penetrator probe to directly sample material. Although this mission is still in the conceptual stage, its very existence shows how seriously the astronomical community is taking the prospect of future interstellar encounters. One of the key hurdles in these missions is speed. Interstellar objects, by definition, are moving faster than most solar system objects. To catch them, we need propulsion systems far more advanced than traditional chemical rockets. Solar sails, which use the pressure of sunlight to accelerate a spacecraft over long periods, are a promising candidate. Concepts like Breakthrough Starshot, which envisions sending wafer-sized probes to nearby stars at a fraction of the speed of light using powerful ground-based lasers, highlight what might be possible in the not-too-distant future. While such technology isn't ready for a near-term interstellar mission, scaled-down versions of solar sail systems could dramatically improve our ability to intercept fast-moving objects within the solar system. There's also discussion of using gravitational assists more strategically. For example, a spacecraft could be sent on a slingshot trajectory around Jupiter or the Sun itself, gaining immense acceleration before redirecting toward the target. The challenge here is timing. Such trajectories must be planned with exquisite precision, and they require advanced knowledge of the object's path. Again, this circles back to why telescopes like Rubin are so crucial. The earlier we detect an interstellar object, the more time we have to design an efficient intercept trajectory. The benefits of such a mission would be profound. Imagine getting close-up images of 3I Atlas, instead of just faint smudges of light in telescope data. We could directly measure its composition, map its surface features, and determine whether it is more like a comet, an asteroid, or something entirely new. We could confirm whether interstellar objects carry organic molecules or water ice, and by extension, test theories about the distribution of life's building blocks across the galaxy. For all the speculation around ʻOumuamua, its shape, its motion, even the wild hypothesis that it might be an artificial object, direct exploration could have provided concrete answers. Future missions offer the chance to turn that speculation into knowledge. There's also a philosophical angle. If interstellar objects are fragments of distant planetary systems, then intercepting one is the closest we can come to sampling another star system, without actually leaving our own. Each visitor is a natural space probe, carrying material across interstellar distances. A successful mission would be like receiving a package from another world, opening it up, and discovering what planetary processes shaped it. In that sense, intercepting an interstellar object isn't just about studying a rock, it's about peering into the environments of alien suns. While no interstellar intercept mission has yet been approved, the momentum is growing. As technology advances and as discoveries like 3I Atlas continue to remind us of what we're missing, it seems inevitable that the day will come when humanity sends a spacecraft to meet one of these mysterious wanderers. The first time we do, it will be one of the most exciting moments in the history of space exploration, our first direct encounter with material from another star. Scientific discovery is rarely a neat, unanimous process. For every major breakthrough, there are usually competing interpretations, heated discussions, and sometimes outright disagreements. Interstellar objects like 1I ʻOumuamua, 2I Borisov, and 3I Atlas are perfect examples of this dynamic. Because they appear suddenly, move incredibly fast, and are observed for only a short window of time, the data we have about them is often sparse. That scarcity leaves room for interpretation, and interpretation inevitably leads to debate. Scientists, driven by curiosity and sometimes differing assumptions, often find themselves in sharp disagreement about what these objects really are, how they formed, and what they mean for our understanding of the galaxy. Perhaps the most famous example of scientific debate surrounding interstellar objects is the case of ʻOumuamua. On the surface, it seems straightforward, an elongated, fast-moving object on a hyperbolic trajectory, clearly from outside the solar system. But the details quickly became contentious. Observations showed that ʻOumuamua was accelerating slightly as it moved away from the Sun, an effect usually associated with outgassing in comets. Yet, no visible gas or dust was detected, which left scientists puzzled. Some argued that it must be outgassing in a way that was invisible to our instruments, perhaps releasing hydrogen or other volatiles that don't produce obvious visual signatures. Others suggested alternative explanations, such as a very thin shape, like a pancake or a shard, responding to solar radiation pressure more strongly than expected. And then, of course, came the most controversial interpretation, that it might be an artificial object, perhaps a probe or debris from an alien civilization. While most astronomers dismissed this as unlikely, the fact that such a possibility was even seriously discussed shows how ambiguous the data was. With 2I Borisov, the debates were less extreme but no less important. Because it looked very much like a comet, complete with a tail and coma, many astronomers saw it as proof that interstellar objects are not necessarily exotic, but could be very similar to familiar solar system bodies. However, disagreements arose about its composition. Spectral observations suggested that Borisov had higher levels of carbon monoxide than most solar system comets, indicating that it might have formed in a much colder environment, possibly on the outskirts of another planetary system. Others argued that the data wasn't conclusive enough to make that determination. Still, the debates around Borisov were more grounded in chemical and dynamical interpretations rather than speculative leaps. When it comes to 3I Atlas, the debates are even thornier, largely because the object was so faint and the data so limited. Some astronomers questioned whether it was truly interstellar at all, suggesting that its orbit might have been miscalculated due to observational uncertainties. While most evidence pointed to a hyperbolic trajectory consistent with an interstellar origin, the faintness of the object left room for skepticism. Even assuming it was interstellar, there were disputes about its classification. Was it more asteroid-like, lacking volatile activity? Or was it a small, inactive comet nucleus that simply didn't get close enough to the Sun to light up with a visible coma? Without clear data on its spectrum, surface brightness, or rotation, the debates remain unresolved. The disagreements don't stop at composition and classification. Astronomers also debate the origins of these objects. Did Oumuamua and Atlas come from the violent outskirts of young planetary systems, where gravitational interactions fling planetesimals into interstellar space? Or did they form in stable environments, gently nudged out over billions of years? Some propose that most interstellar objects originate in binary star systems, where the gravitational dynamics are particularly efficient at ejecting material. Others argue that they could come from single-star systems much like our own. Still others speculate that they could be remnants of catastrophic events, like collisions between icy bodies or even fragments from disrupted planets. With each new interstellar object, the theories multiply, but so far the data hasn't been able to narrow them down definitively. Even their shapes are a matter of contention. Oumuamua's light curve suggested it was extremely elongated, possibly 10 times longer than it was wide. But this interpretation depends heavily on assumptions about its rotation, reflectivity, and surface texture. Some scientists think it could have been more pancake-shaped. Others argue it could have been a loose, fractal-like aggregate of dust and ice. The truth is, without direct imaging, we simply don't know. 3I Atlas, being even fainter, leaves even less certainty about its size or shape, so the debates are even more speculative. There's also a meta-debate. How much should we entertain extraordinary explanations for these objects? Some astronomers argue that we should stick strictly to natural, well-understood astrophysical processes, resisting the temptation to invoke exotic scenarios like alien technology. Others counter that science advances by considering all possibilities, however unlikely, and that dismissing unconventional ideas too quickly risks overlooking something truly revolutionary. This tension, between cautious conservatism and bold speculation, runs through nearly every discussion of interstellar objects. The fascinating thing is that these debates aren't a sign of weakness in science, they're a sign of its vitality. Astronomy is dealing with phenomena we've only just begun to observe. Disagreements are inevitable when data is limited, and they often drive new ideas, new instruments, and new missions. For example, the debates about Oumuamua's acceleration have spurred renewed interest in solar sail dynamics and unusual cometary compositions. The discussions around Borisov's chemistry have inspired comparisons with early solar system models. And the uncertainty about Atlas underscores the urgent need for more powerful surveys and fast response missions. What unites all of these debates is a shared recognition of how little we truly know. Each interstellar object is a messenger from beyond, carrying secrets from distant star systems. But with every discovery, instead of answering all our questions, we often end up with more questions than we started with. This is both frustrating and exhilarating. It means there's still so much left to uncover, and that future discoveries will continue to surprise us. When the first interstellar object, Oumuamua, was spotted in 2017, it felt like a once-in-a-lifetime discovery. For centuries, astronomers had wondered if fragments of other star systems might drift into ours, but until then it was purely speculation. Then, just 2 years later, 2I Borisov was detected, followed not long after by the possible third candidate, 3I Atlas. That rapid sequence of discoveries forced astronomers to rethink their assumptions about just how rare, or common, interstellar visitors actually are. Instead of being once-in-an-era events, these objects might be slipping through our solar system much more often than we ever realized. The challenge isn't that they're rare, it's that they're hard to see. The rarity question begins with basic physics. Every star system forms with countless small icy and rocky bodies left over from the planet-building process. In our own solar system, these leftovers exist as the asteroid belt and the Kuiper belt, with trillions of comets residing in the distant Oort cloud. When planets and other large bodies tug on these small objects gravitationally, some get flung out entirely, escaping into interstellar space. If this happens in our system, it surely happens in others. Given that our galaxy contains hundreds of billions of stars, the number of interstellar wanderers adrift between systems must be unimaginably vast. So the real question is not whether they exist, but how often they wander into our tiny observational field of view. Early estimates following Oumuamua's discovery suggested that perhaps one interstellar object the size of Oumuamua passes through the inner solar system every year. That was a shocking revision from earlier thinking, which had assumed they would be far rarer. When 2I Borisov was found in 2019, it lent credibility to that higher frequency estimate. Then came 3I Atlas, which, though faint and uncertain, added more weight to the argument. Each detection has made astronomers increasingly confident that the solar system is routinely visited by material from distant stars, and that we've simply been blind to it until recently because our telescopes weren't sensitive enough. There are also population estimates based on the physics of ejection. Models suggest that each star may eject billions of small bodies over its lifetime, especially during the chaotic early periods of planet formation. When giant planets like Jupiter or Saturn shift positions in a system, they act like gravitational slingshots, hurling comets and asteroids into interstellar space. If even a fraction of all stars do this, the galaxy should be littered with trillions of such objects, drifting silently between the stars. That means the solar system is likely being crossed by many of them at any given moment. Most are too small, too faint, or too far from Earth to detect, but they are out there. Astronomers also debate how big these visitors usually are. Oumuamua was relatively small, perhaps a few hundred meters long, while Borisov was more like a kilometer across. If larger objects pass through, they might be visible for longer and easier to study, but they are likely much rarer. Smaller ones, on the other hand, could be incredibly common, passing through the solar system by the dozens or even hundreds each year, but too dim to notice with our current instruments. This is why improved sky surveys are so important. They could reveal a whole hidden population of interstellar debris constantly moving through our celestial neighborhood. One intriguing point is that we might already be finding fragments of interstellar material without realizing it. In recent years, a few meteor events on Earth have been re-examined, and some researchers suggest that at least one of them, a fireball detected over Papua New Guinea in 2014, might have been interstellar in origin. The US Space Command even confirmed that the object's speed was so high that it likely came from outside the solar system. If true, that means interstellar material doesn't just pass through the solar system, it sometimes collides with Earth's atmosphere, giving us fleeting glimpses, or even physical samples, of other star systems. Of course, these numbers come with caveats. Our sample size is still tiny, just a handful of confirmed candidates. That makes the statistics fuzzy and prone to revision. Some astronomers argue that Oumuamua and Borisov might have been lucky finds, and that the actual rate of interstellar visitors is lower. Others counter that with upcoming observatories, like the Vera Rubin Observatory, we'll soon see dozens of them every decade, proving that they're far more common than skeptics assume. The truth probably lies somewhere in between, not as rare as once thought, but not as abundant as the most optimistic projections suggest. What's clear is that interstellar objects are not once-in-a-century oddities. They are part of the ongoing traffic of the galaxy, the natural byproducts of planetary formation scattered across space. Our solar system is not isolated. It is porous, constantly intersected by material from other systems. Each detection is like catching a visitor passing through a busy cosmic crossroads, and the more we watch, the more we realize how much activity is happening around us. The rarity debate ultimately ties into a deeper question. What can these objects teach us? If they are common enough to study regularly, they could open an entirely new branch of astronomy, comparative planetesimal science, where we don't just study our own asteroids and comets, but directly compare them to those born under alien suns. That's why estimates of rarity matter so much. They tell us whether 3I Atlas was a fleeting fluke, or a sign that the galaxy is constantly sending us new samples to study. For centuries, interstellar objects were the stuff of speculation. Astronomers assumed they must exist. After all, gravity in young planetary systems should fling countless icy fragments into the void, but no one had ever actually seen one. The main obstacle wasn't rarity, it was visibility. These visitors are small, faint, and incredibly fast, slipping through the solar system before anyone has a chance to notice. But in just the past decade, the story has changed. The reason is not that interstellar objects suddenly started arriving in greater numbers. It's that our tools for spotting them have finally become sensitive enough to catch them in the act. The first major technological breakthrough has been the rise of wide-field survey telescopes. Instead of focusing on narrow slices of the sky at high magnification, These instruments sweep across enormous sections of the heavens night after night, comparing new images to previous ones. This makes them especially good at detecting moving objects, whether they're near-Earth asteroids, distant comets, or the rare hyperbolic wanderer from another star system. Oumuamua was discovered in 2017 thanks to the Pan-STARRS survey in Hawaii, a telescope array specifically designed for this kind of sky monitoring. Without such technology, it would have slipped by unnoticed, just one more anonymous speck of light lost in the sky's vastness. The Atlas survey, which later detected 3I Atlas, operates on a similar principle but is optimized for speed. Its mission is planetary defense, to catch asteroids headed toward Earth before they get too close. That requires scanning the entire visible sky multiple times per night, looking for anything that shifts against the backdrop of stars. This rapid cadence dramatically increases the odds of catching unusual objects, including interstellar ones. In fact, Atlas was not explicitly designed to find interstellar objects. It simply stumbles upon them as part of its broader goal of asteroid detection. That illustrates a key point. The rise in interstellar detections is often a byproduct of investments in Earth safety and asteroid defense. Another reason detection is growing is the advancement in automated data analysis. A modern survey telescope can generate terabytes of data in a single night, far more than human astronomers could sift through manually. Machine learning algorithms and automated pipelines now do the heavy lifting, comparing images, flagging anomalies, and ruling out false positives. This automation allows astronomers to spot faint, fast-moving objects in near real time. When Pan-STARRS first saw Oumuamua, it took only a short time for the software to flag its unusual trajectory. Likewise, Atlas's automated pipeline was able to recognize the motion of 3I Atlas, even though it was faint and only briefly visible. Without these computational advances, many interstellar objects would remain hidden in the overwhelming flood of sky survey data. Improvements in detector technology have also been crucial. Older telescopes relied on photographic plates or early-generation CCDs that lacked the sensitivity to pick up very dim objects. Today's detectors are vastly more efficient, capable of capturing more light with shorter exposures. That means survey systems can see fainter objects farther out, extending the range at which an interstellar visitor might first be spotted. The earlier we notice one, the longer we have to study it before it vanishes into interstellar space again. Connectivity is another factor that has transformed detection. Once an unusual object is flagged, astronomers around the world can coordinate within hours, using networks of telescopes to confirm observations, refine orbital calculations, and secure follow-up data. The Minor Planet Center, for example, acts as a clearinghouse where detections are logged and distributed globally. This rapid response system means that even faint or borderline detections, like 3I Atlas, can be confirmed and tracked before they're lost. In an earlier era, without such international coordination, many of these fleeting objects would have been missed. There's also a sociological element at play. Ever since the discovery of Oumuamua, astronomers have been primed to look for more interstellar candidates. The excitement of that first find dramatically raised awareness, and observatories are now more likely to scrutinize unusual trajectories rather than dismiss them as errors or unremarkable comets. In a sense, the discovery of Oumuamua trained the scientific community to recognize the signature of an interstellar interloper. That heightened awareness, combined with better tools, has made each subsequent detection more likely. The growing detections also benefit from cross-mission synergy. Space telescopes, like the Hubble and Spitzer observatories, have provided follow-up data that ground-based surveys alone couldn't capture. Meanwhile, upcoming missions like the James Webb Space Telescope are poised to provide detailed compositional data if future interstellar objects are caught early enough. As survey systems flag new candidates, these high-powered instruments can pivot to study them in depth. This layered approach, wide-field detection followed by high-resolution study, represents a major leap forward compared to what was possible just a few decades ago. All of these advances are converging at just the right time. In the past, astronomers may have been watching the sky, but they were essentially doing it blindfolded, looking at tiny patches of space with relatively crude detectors. Now, with global networks of telescopes, sensitive CCD arrays, machine learning, and rapid international coordination, the chances of catching interstellar objects have never been higher. The reason discoveries like 3I Atlas are becoming more common isn't that the galaxy suddenly started delivering more visitors. It's that we finally built the tools to notice them. And we're only at the beginning. Each step forward in technology increases the number of faint objects we can see, which in turn increases the likelihood of detecting even smaller and dimmer interstellar visitors. With new observatories on the horizon, the detection rate is expected to skyrocket, transforming interstellar objects from rare anomalies into a regular part of astronomy. The growth in detection isn't just a story of better telescopes. It's the story of humanity learning to peel back another layer of the universe, finally noticing the quiet flow of material drifting between the stars. When ʻOumuamua was first announced in 2017, it became a cultural sensation almost overnight. It wasn't just an astronomical discovery, it captured the imagination of the public in a way very few scientific events ever do. Headlines around the world blared about the first interstellar visitor, and almost immediately, debates erupted about what it might be. Its unusual elongated shape, bizarre acceleration that didn't fit standard comet models, and the mystery of its composition led to speculation that went far beyond science journals. Prominent figures, including Harvard astronomer Avi Loeb, even suggested that ʻOumuamua might be artificial, perhaps a fragment of alien technology. Whether people believed that or not, the suggestion ensured that ʻOumuamua stayed in the public consciousness, covered not just in scientific circles but in mainstream news, podcasts, YouTube videos, and even late-night talk shows. By contrast, 3I Atlas received nowhere near that level of attention. When its discovery was reported, it made headlines in niche science outlets and astronomy communities, but it didn't explode into the mainstream the way ʻOumuamua did. There are several reasons for that difference, and they tell us a lot about how science is received by the public. The first and most obvious reason is the element of mystery. ʻOumuamua's odd behavior practically invited wild speculation. It didn't fit cleanly into the categories of asteroid or comet. Its strange shape and unexplained acceleration were puzzles without satisfying answers, and people are naturally drawn to mysteries. By contrast, 3I Atlas, while intriguing to astronomers, appeared much fainter, less distinctive, and didn't stick around long enough to generate the same kind of buzz. Without strong visual images or unusual behavior to grab attention, it simply didn't spark the imagination in the same way. Another factor is timing. By the time 3I Atlas was discovered, the novelty of interstellar objects had already been broken by ʻOumuamua and 2I Borisov. The first time something happens, it's a landmark event. The third time, it feels more like confirmation than revelation. Astronomers were excited, of course. It suggested that interstellar objects may be more common than previously thought, but for the general public, the wow factor had diminished. News editors and social media users are always searching for fresh stories, and third interstellar object spotted simply didn't have the same ring to it. There's also the issue of visibility and data quality. ʻOumuamua, though small, was bright enough and present long enough to allow a relatively detailed study. That gave scientists something to argue about and the media something to report. 2I Borisov, the second interstellar object, was even more spectacular. It behaved like a comet, grew a visible tail, and provided clear data for astronomers to study. But 3I Atlas was much fainter, seen for only a short period of time, and difficult to analyze in detail. That made it less visually compelling for the public and less controversial within the scientific community. If a discovery doesn't provide striking images or unanswered mysteries, it struggles to break into mainstream attention. The role of public imagination shouldn't be underestimated here. ʻOumuamua coincided with a cultural moment when discussions about alien life, space exploration, and the mysteries of the cosmos were already front and center. Popular science books, movies, and even the push toward private spaceflight had primed people to pay attention to anything otherworldly. ʻOumuamua fed directly into those narratives. 3I Atlas, on the other hand, didn't challenge our imagination in the same way. It wasn't cigar-shaped, it didn't act strangely, and it didn't inspire bold claims about extraterrestrials. Without that what-if factor, the story remained largely confined to those already following astronomy news. Even within the scientific community, the reaction was more muted. ʻOumuamua spurred an avalanche of papers, workshops, and debates, partly because it was the first of its kind and partly because it raised so many unanswered questions. 2I Borisov also generated extensive research, thanks to its comet-like appearance and relatively long visibility. 3I Atlas, though scientifically valuable, was harder to study due to its faintness and short observational window, which meant fewer published papers and less fuel for ongoing debate. In science, the more data an object produces, the more sustained the discussion, and 3I Atlas simply didn't deliver enough material to keep the conversation alive. Still, among dedicated astronomy enthusiasts and professionals, the discovery of 3I Atlas was an exciting confirmation that interstellar visitors are likely not once-in-a-lifetime events. While it didn't make front-page news, it strengthened the growing realization that our solar system is far from isolated. In some ways, the quieter public reaction reflects a shift. Interstellar objects are becoming normalized. Where once they seemed impossible, now they are expected, even routine. This contrast between public reaction to Oumuamua and 3I Atlas highlights a broader truth about how scientific discoveries resonate. It's not just about what's discovered, it's about the story around it. Oumuamua had mystery, controversy, and novelty. 3I Atlas had quiet confirmation and subtle significance. Both are important, but only one captured the collective imagination. When interstellar objects enter our solar system, they immediately capture both scientific and public imagination. And with that excitement often comes a wave of misconceptions. This was especially true for Oumuamua, which became the subject of intense speculation about alien spacecraft, advanced probes, or artificial technology. By the time 3I Atlas was discovered, that atmosphere of curiosity and sensationalism lingered in the public mind. Some people automatically wondered whether it might also be evidence of extraterrestrial intelligence. But the truth is much less dramatic. 3I Atlas, while fascinating, shows no signs of being artificial. To understand why these misconceptions arise, it's important to look back at what fueled the alien debates around Oumuamua. That object exhibited unusual behavior. It had no visible tail like a comet, its shape seemed extreme and elongated, and most mysteriously, it appeared to accelerate in a way that didn't match simple gravitational predictions. Those anomalies gave rise to headlines suggesting it might be a solar sail or some kind of probe. Harvard astrophysicist Avi Loeb famously argued that we should take the alien hypothesis seriously, and his views spread widely outside the scientific community. With 3I Atlas, however, no such anomalies were observed. It didn't have the strange acceleration that fueled theories about Oumuamua. It didn't stick around long enough to spark debates about shape or structure. And its faintness meant that while it was difficult to study, it didn't give off puzzling or contradictory data that would invite exotic explanations. The limited information scientists gathered pointed toward it being a natural body, probably an icy fragment similar to a comet, though less active than Borisov and less dramatic than Oumuamua. One common misconception people have is the assumption that because something is interstellar, it must be exotic. In reality, interstellar simply means it originated outside our solar system, not that it's made of mysterious materials or alien technology. When young planetary systems form, they tend to eject a huge number of comets, asteroids, and icy fragments through gravitational interactions with giant planets. These fragments drift through the galaxy, and occasionally, one passes through our solar system. There's nothing inherently artificial about that process. It's just astrophysics on a galactic scale. Another misconception is that astronomers are hiding or downplaying alien evidence. This suspicion often comes from the frustration that many discoveries, including 3I Atlas, are faint and incomplete, leaving people to fill in the gaps with imagination. But astronomers are generally transparent about what they know and don't know. In the case of 3I Atlas, the main limitation was the lack of data. It was simply too faint and too fleeting to study in great detail. That doesn't mean there was something secret or suspicious about it. It just means the technology at hand wasn't able to gather more. Some have also confused the designation Atlas with deliberate naming by scientists trying to hint at hidden truths. In reality, the name comes from the telescope system that discovered it, the Asteroid Terrestrial Impact Last Alert System. There was no coded message, no mythological allusion implying alien origin. It was simply catalogued following established naming conventions. The 3I designation is a straightforward reference to it being the third interstellar object detected. It's also worth pointing out that if an interstellar object did display truly artificial characteristics, such as regular radio emissions, perfectly geometric shapes, or propulsion inconsistent with natural physics, it would likely be one of the biggest discoveries in human history, and scientists would leap at the chance to study it. The fact that researchers did not make such claims about 3I Atlas is telling. They didn't ignore anything unusual. There was simply nothing unusual to ignore. This is not to say interstellar objects aren't scientifically exciting. They absolutely are. Each one provides us with rare physical evidence of other star systems, offering a chance to study materials that were formed under alien suns. But that excitement should not be confused with proof of extraterrestrial intelligence. Natural explanations fit the observations of 3I Atlas far better than any artificial hypothesis. In short, while the discovery of 3I Atlas might inspire people to wonder about alien technology, the reality is much simpler. It was a faint, fleeting, natural fragment from another solar system. Its study contributes to our understanding of interstellar debris, not alien engineering. Misconceptions often arise from the hunger for mystery and the lack of detailed data, but astronomers are clear. There is no evidence whatsoever that 3I Atlas was artificial or alien in nature. Even though 3I Atlas was faint, fleeting, and offered astronomers only a very short window of study, it still managed to teach us valuable lessons. In astronomy, sometimes the most important insights don't come from overwhelming amounts of data but from small confirmations that reshape our expectations of the universe. That was certainly the case here. What scientists gained from 3I Atlas was not just information about the object itself, but a deeper understanding of what interstellar visitors mean for our solar system, for planetary science, and for the galaxy at large. The first and perhaps most crucial lesson is about frequency. Before ʻOumuamua's discovery in 2017, interstellar objects were considered possible in theory but unlikely to ever be observed. The idea that a chunk of rock or ice could cross interstellar space and wander through our solar system was discussed in academic papers, but without concrete evidence, it felt like speculation. ʻOumuamua shattered that assumption, and then 2I Borisov confirmed it. But with 3I Atlas appearing only a couple of years later, astronomers began to realize something profound. These objects are not rare, once-in-a-lifetime events. They may be relatively common, even passing through the solar system regularly, unnoticed until recently. This shifted the perspective from occasional miracles to an ongoing opportunity. The second lesson was about detection limitations. 3I Atlas was so faint and so quick to fade that it revealed how fragile our observational capabilities still are. Despite having a network of sky surveys and advanced telescopes, astronomers barely caught sight of it before it was gone. This drove home the point that for every interstellar object we spot, there could be many others slipping past us undetected. The faintness of 3I Atlas underscored the need for larger, more sensitive telescopes and wider sky coverage. It essentially served as a wake-up call. If we want to truly understand the traffic of interstellar debris through our neighborhood, we need better tools. Another lesson was about diversity. Each of the 3 interstellar objects observed so far has been strikingly different. ʻOumuamua was small, elongated, and strangely lacking a cometary tail. Borisov, by contrast, was unmistakably a comet, with a bright coma and tail, behaving much like the comets we see regularly within our solar system. 3I Atlas, meanwhile, was faint, less active than Borisov, and quickly faded. This variety suggests that interstellar objects are not a uniform population. Instead, they are as diverse as the asteroids and comets we find here at home, reflecting the wide range of conditions in the planetary systems where they originated. That's an important clue. It tells us that other solar systems produce debris similar to our own, but with their own unique fingerprints. A subtler but important lesson came from the limits of interpretation. With ʻOumuamua, scientists debated vigorously about its shape, origin, and behavior, largely because they had enough data to fuel those debates. With 3I Atlas, there wasn't enough data to spark that kind of controversy. This highlighted the reality that sometimes science must accept ambiguity. Not every discovery will yield clear answers, and sometimes what we learn is simply that we need to be faster and better prepared next time. In that sense, 3I Atlas became a case study in humility, a reminder that the universe doesn't always present its mysteries in neatly packaged, easily studied forms. Perhaps one of the more inspiring lessons is that even limited encounters matter. The faint light captured from 3I Atlas might not have revealed its exact size, shape, or composition, but it still added a data point to the growing body of evidence about interstellar travelers. Science often advances not through dramatic singular events, but through accumulation. Each observation, no matter how small, helps build the larger picture. With 3i Atlas, the lesson is that every visitor counts, even if its story remains incomplete. It also reinforced the importance of preparedness for future opportunities. If we can detect these objects earlier, we may one day be able to redirect large telescopes, spectrographs, or even spacecraft toward them in time to gather detailed information. 3i Atlas taught us what happens when we're just a bit too slow or too limited. The moment passes, and with it the chance for deeper study. The takeaway for astronomers is clear: being ready is everything. Finally, 3i Atlas reminded scientists and the public alike of the cosmic interconnectedness of planetary systems. Every interstellar object is a piece of another star's story, a fragment of worlds that formed far away and long ago. Even without precise data, the fact that 3i Atlas made it here at all is remarkable. It means that the solar system is not an isolated bubble but part of a galactic ecosystem, constantly intersected by material from other suns. This realization may be its most profound lesson. Our story as a solar system is interwoven with countless others across the Milky Way. So while 3i Atlas may not have left us with detailed charts of composition or dramatic debates about alien probes, it left us with lessons about frequency, diversity, limitations, and the urgent need for readiness. It reminded us that science is not always about clear answers but about building knowledge piece by piece. And in that way, it played a crucial role in preparing humanity for the many interstellar visitors yet to come. When we step back and place 3i Atlas into the broader context of interstellar exploration and discovery, its importance becomes much clearer. On its own, it might seem like a faint, fleeting smudge of light, barely detected and quickly gone. But when considered alongside ʻOumuamua and Borisov, and within the larger history of how humanity has imagined and studied interstellar space, 3i Atlas becomes a piece of a much larger and deeply fascinating puzzle. It's part of a growing narrative that is reshaping how we think about the solar system's connection to the rest of the galaxy. For most of human history, the idea of objects traveling between star systems was confined to the realm of theory and imagination. Ancient cultures looked up at the stars and saw them as eternal, fixed points of light. Even as astronomy advanced, the notion that fragments of other solar systems might pass through ours wasn't something we could prove. Astronomers assumed the solar system was mostly self-contained, with its asteroids, comets, and planets forming an isolated neighborhood. It wasn't until the 20th century that the possibility of interstellar objects gained traction scientifically, as models of planetary system formation suggested that many systems should eject vast numbers of icy bodies into interstellar space. Yet, without direct detection, interstellar objects remained in the shadows of speculation. That changed dramatically with 1i ʻOumuamua in 2017. Its sudden appearance marked the first time humanity had irrefutable evidence that material from another star system had entered our own. That discovery was a watershed moment. It confirmed centuries of theoretical predictions and turned interstellar objects from hypothetical to real. Suddenly, astronomy was no longer about asking if such visitors existed but about understanding how many there are, what they look like, and what they can tell us. 2i Borisov followed just 2 years later, in 2019, reinforcing the idea that these objects are more common than once assumed. While ʻOumuamua left scientists puzzled with its unusual behavior, Borisov behaved much like a normal comet, only it came from another star system. Together, they established the beginning of a new field of research: interstellar object studies. The discovery of 3i Atlas, faint though it was, is the continuation of that story. It's the third chapter in a saga that's still unfolding, showing that our solar system is far from isolated. In this broader narrative, 3i Atlas plays a subtle but significant role. It demonstrates that these objects can be very faint, hard to detect, and fleeting in nature. That, in turn, emphasizes the necessity of building a systematic approach to interstellar object science. Each discovery so far has been serendipitous. Astronomers happen to catch sight of the objects just as they pass through. But as we look forward, the goal is to move from luck to preparedness, turning chance discoveries into deliberate opportunities. 3i Atlas helped underscore that urgency. Placing 3i Atlas into the context of exploration also reminds us of the extraordinary distances these objects travel. Each interstellar visitor is like a cosmic messenger, carrying material forged under the influence of a distant sun. Unlike light or radio waves, which are immaterial signals, these objects are physical, solid pieces of another system, ejected long ago and wandering across interstellar space. Studying them is, in effect, a form of contact with alien worlds. That's not science fiction. It's the reality of planetary science in the 21st century. And in that way, 3I Atlas, despite being faint, belongs to a category of discoveries that fundamentally expand our cosmic perspective. There's also a broader cultural context worth noting. The discovery of ʻOumuamua, Borisov, and now 3I Atlas has come at a time when humanity is increasingly invested in space exploration, through Mars missions, private spaceflight, and plans for future deep space probes. Interstellar objects connect to these ambitions because they highlight the idea that our solar system is not alone. They remind us that other systems exist, that they too produce comets and asteroids, and that someday, humanity might venture far enough to see those star systems up close. In that sense, each object is both a scientific discovery and a symbolic bridge to the stars. Even though 3I Atlas was not as well observed as its predecessors, it adds to this cultural and scientific momentum. Together, the three interstellar objects represent a turning point in how we view our relationship with the galaxy. They are no longer curiosities but signposts on the road toward interstellar science. Each one tells us something different. ʻOumuamua about the strangeness and unpredictability of interstellar debris, Borisov about the familiar patterns of cometary behavior across systems, and 3I Atlas about the challenges and limitations of current detection methods. The broader context also includes the future. The story of interstellar exploration is just beginning, and 3I Atlas is part of that origin. Future telescopes like the Vera Rubin Observatory, future missions designed to intercept fast-moving visitors, and future generations of astronomers will build upon these first few encounters. When historians of science look back 100 years from now, they may see the late 2010s and early 2020s as the dawn of interstellar object science, a moment when humanity first began to see and study fragments of other worlds drifting into our skies. In that story, 3I Atlas, faint though it was, will still have its place. So, in the broader context of interstellar exploration, 3I Atlas is not just a minor, underwhelming discovery. It is a crucial link in a chain of evidence proving that our solar system is part of a dynamic galactic environment, constantly intersected by material from elsewhere. It shows us that we're only scratching the surface of what's out there and that each detection, no matter how faint, brings us one step closer to understanding the galaxy we live in. When it comes to 3I Atlas, perhaps the most compelling aspect is not what we know, but what we don't know. Unlike ʻOumuamua, which gave us strange data to argue over, or Borisov, which showed us a textbook-like example of a comet from another star system, 3I Atlas left us with almost nothing concrete. Its faintness and brief visibility meant that astronomers had only the smallest sliver of time to collect information, and even then, the data they captured raised more questions than it answered. These unknowns are not failures of science. They're the mysteries that keep scientists intrigued, the gaps that push astronomy forward. The first big unknown is its size. Estimates vary widely, with some astronomers suggesting it may have been only a few tens of meters across, while others argue it could have been substantially larger. The faintness of the object made it nearly impossible to measure directly. Was it a small, dim fragment that happened to be passing through, or a larger body that was unusually dark and reflective? Without better data, we can't say. This ambiguity itself is fascinating because size determines not just the nature of the object but also the likelihood of detecting others like it. Closely tied to that is the unknown of its composition. With Borisov, astronomers could analyze the gases it released and identify familiar chemical signatures. With ʻOumuamua, scientists at least debated whether its strange acceleration was due to outgassing or some exotic form of ice. But with 3I Atlas, there was no such luxury. The faint light didn't provide enough spectral data for chemical analysis. Was it made primarily of rock? Ice? A mixture of the two? Did it have unusual compounds from a faraway system? We don't know. This gap leaves open tantalizing possibilities. 3I Atlas could have been fairly ordinary, or it could have been composed of exotic materials we've never seen in our solar system. Another major unknown is its origin. Every interstellar object sparks the question, which star system did it come from? With ʻOumuamua and Borisov, astronomers attempted to trace their trajectories backward to see if they could be linked to known stars or stellar nurseries. The chaotic gravitational influences of planets make that difficult, but at least some candidates were considered. For 3I Atlas, however, the data was too thin. Its hyperbolic orbit proves it came from outside the solar system, but which direction it truly originated from remains hazy. Was it flung out of a young star system still forming planets? Or was it ejected billions of years ago during the early chaos of a distant system's history? These unanswered questions highlight just how little we know about the galactic pathways of such objects. There's also uncertainty about its activity. Normally, if an object contains volatile ices, sunlight should cause it to release gas and form a coma or tail. Borisov, for instance, displayed this classic behavior. ʻOumuamua, strangely, didn't, sparking debates about hidden outgassing or alternative explanations. 3I Atlas, however, was too faint to determine definitively whether it was outgassing or not. Did it behave like a comet at all, or was it inert like an asteroid? The lack of clarity is frustrating, but it's also intriguing. It suggests there may be a wide spectrum of interstellar object behaviors, from highly active to completely inactive, and we simply don't know where 3I Atlas fits. Another unknown is the reason for its faintness. Was it truly just a very small body, or was its surface covered in material that reflected very little light? Could it have been tumbling in such a way that we caught it at a poor angle? Or was it simply moving at a distance that made it hard to see? The truth could be any combination of these factors, and without more observations, the question remains unresolved. Yet the faintness itself is an important clue. It might mean that the galaxy contains vast numbers of interstellar objects too dim for us to see, making 3I Atlas just the tip of the iceberg. We also don't know much about its shape. ʻOumuamua captured imaginations because its shape was inferred to be elongated or possibly pancake-like, sparking endless debates. Borisov appeared more spherical, like most comets. 3I Atlas, however, was too faint and too briefly observed to even speculate. Its light curve didn't provide enough evidence to suggest whether it was irregularly shaped or relatively uniform. This lack of detail is a blank space in the record, another reminder of how much slipped past us. Then there's the question of its future. We know it's leaving the solar system on a hyperbolic trajectory, but where will it go? Will it drift endlessly between stars, or might it eventually be captured by another system's gravity? Could it one day collide with a planet or star far away? The life stories of interstellar objects are long and unknowable, and with 3I Atlas, we'll never know its exact fate. Perhaps the most intriguing unknown, though, is the broader population it represents. Each interstellar object we discover raises the question of how many more are out there. If ʻOumuamua, Borisov, and 3I Atlas appeared within just a few years, does that mean these visitors are constantly passing by, most of them unseen? 3I Atlas, with its faintness, suggests that many interstellar travelers may simply escape our notice. How many have already slipped by, invisible to our telescopes? How many are drifting through the outer solar system right now? The true scale of this unseen population remains one of the great unknowns of modern astronomy. All of these mysteries, its size, its composition, its origin, its activity, its shape, its population context, make 3I Atlas far more intriguing than it might appear at first glance. While it didn't give us the wealth of data that ʻOumuamua or Borisov did, its very obscurity is a lesson in itself. It's a reminder that science isn't about having all the answers but about asking better and deeper questions. 3I Atlas leaves us with questions that will drive future discoveries, fueling the excitement for the next interstellar visitor that graces our skies. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.